So now the next question is, a separately excited DC machine supplies a load current of 50 ampere at a terminal voltage of 220 volt. Its RA is equal to 0.2 ohm. This machine is running as a motor with the same terminal voltage and current at the same speed. If Φm is the flux when run as motor and Φg is the flux when run as generator, then what is the ratio of the Φm by Φg? So a separately excited DC machine supplies a load current of 50 ampere at a terminal voltage of 20 volt. Its RA is equal to 0.2 ohm. This machine is run as a motor with the same terminal voltage and current at the same speed. If Φm is the flux when run as a motor and Φg is the flux when run as a generator, then what is the ratio of Φm by Φg? So basically this DC machine, we are going to operate as a generator and also as a motor. In this question they are given the terminal voltage is equal to 220 volt and the load current is equal to 50 ampere. So this is for both for the generator and also for the motor. So now we have to find, see, we know the terminal voltage and terminal current are same, but the only thing is here for the separately excited DC machine, the only thing that we have to make sure that whatever the speed that we are going to rotate is also same. If this is the conditions, then what is the ratio of the Φm by Φg we need to figure out. It is option B, which is 0.913 is the correct solution of this question. So let's solve this numerical. So let me first go for the generator part. It is separately excited means separately we are going to give a field winding of current IF1. So this is the field current IF1 which is generating a flux of Φg. So I am going to rotate at a speed of Ng for this rotor. I am going to rotate the shaft at a speed of Ng. So I am going to get a back EMF of Eg. I am going to generate a voltage of Eg. So this is the armature resistance. And in the question they are given the terminal voltage is equal to 220 volt and the load current is equal to 50 ampere. And the armature resistance is equal to 0.2 ohm. So if you apply the KVL, we are going to get Eg is equal to IL into Ra plus Vt. So you know the value of IL, you know the value of Ra, and you also know the value of Vt. So substitute here, we will get the value of Eg. So IL is equal to 50 ampere, Ra is equal to 0.2, Vt is equal to 220. If you keep all these values and if you solve this one, we are going to get the EMF which is generated is equal to 230 volt. So for the same machine, now we are going to operate in the DC motor, in the motoring mode. So now we are going to give a field current of IF2, the flux produced is Φm. So now we are going to give the same terminal voltage of 220 volt and the input current is same current as the previous one, which is 50 ampere. So this is the Ra, the back EMF is Eb. So it is going to rotate at a speed of Nm. In the question they are given that the speeds are same for the both the things. So Nm is equal to Nj. The speed in generated mode is equal to speed in the motor mode. In the question they have already mentioned this one. So now we know the Vt, we know IL, we know Ra. So now we have to find what is the value of the back EMF Eb. So Eb is equal to Vt minus IL into Ra. Vt is equal to 220, IL is equal to 50 and Ra is equal to 0.2. So if we substitute all these values and if we simplify, we are going to get Eb is equal to 210 volt. So in a DC machine, the basic equation, the basic EMF induced is equal to P5 into N by 60 into Z by A. If you see clearly, E is proportional to phi only because M is the same. M is same for both generating mode and also the motoring mode. So E is proportional to flux only. So therefore, Eb by Eg is equal to Φm by Φg because Eb is the back EMF induced in the motoring mode. Eg is the EMF generated in the generating mode. So here Φm is the flux in the motoring mode and Φg is the flux in the generating mode. So Eb by Eg is equal to Φm by Φg. So we know the value of Eb 210, Eg is 230. So this ratio is equal to Φm by Φg. So Φm by Φg is equal to, if you solve this ratio, we are going to get 0.913. So this is the correct solution of this question. So now the next question is, if the real power demand is suddenly increased, the frequency of the system will. See, if the real power demand is suddenly increased on the system, then what is the frequency of the system will happen? It will decrease. So whenever the power demand is increased, the frequency of the system will decrease. Suppose if the power demand is decreased, means the frequency of the system will increase. Both are always inversely proportional. So whenever the real power demand on the system is increased, means the frequency will decrease. Or if the real power demand on the system is decreased, means the frequency will increase. So here the option C is the correct solution of this question. So now let us discuss something more about this one. So you can see clearly here, the increased load is initially met by stored kinetic energy. So whatever the increased load, that increased load we are going to meet with the help of the stored kinetic energy in the rotor. So now due to load present for more time, then the kinetic energy decreases, so frequency also decreases, because kinetic energy is always proportional to frequency square. So therefore simply we can say that whenever the load is increased, initially whatever that load demand we can meet the demand with the help of stored kinetic energy in the rotor. But as the load demand is present for a lot amount of time, then gradually the kinetic energy will decrease. So therefore the frequency also decreases, because kinetic energy is always directly proportional to square of the frequency. So therefore whatever the increased load is, initially we are going to meet it with the help of stored kinetic energy in the rotor. But as the load we are going to present for a lot of amount of time, so therefore the kinetic energy of the rotor will decrease. So therefore the frequency of the system is also going to decrease, because kinetic energy is always directly proportional to square of the frequency. So you can see clearly here, as the load demand increases, I have already told you, whenever the load demand increases, the kinetic energy of the rotor decreases. So therefore the frequency of the system will decrease. Similarly, the vice versa, as the load demand decreases, the kinetic energy of the rotor increases, so frequency also increases. So you can easily know with the help of this plot of the diagram. So you can see clearly, as the power demand increases, the frequency of the system will decrease. As the power demand decreases, the frequency of the system will increase. You can see clearly from this diagram also. So whenever the load demand, the active real power or the real power demand increases, the frequency of the system will decrease. Or if the power demand is the active real power demand decreases, then the frequency of the system will increase. You can see clearly from this pictorial graph also. So finally I can say that whenever the load demand increases, the kinetic energy of the system decreases, so frequency will decrease. Similarly, whenever the load demand decreases, the kinetic energy increases, so frequency increases. You can see clearly from this diagram also, as the active real power demand increases, the frequency decreases, or if the active real power demand decreases, then the frequency of the system will increase. So now we are going to see another question. Two generators rated at 200 megawatt and 400 megawatt are operating in parallel. Their governor group characteristics are respectively 4% and 5% from no load to full load. At no load, the system frequency is 50 Hz. When supplying a load of 600 megawatt, the system frequency is we need to figure out. So here basically they have given two generators. Let me assume G1 of rating of 200 megawatt and G2 of 400 megawatt. They are going to operate in parallel. So for the G1, it is going to have a governor group characteristics of 4% from no load to full load. And for G2, we are going to have a 5% from no load to full load. And initially at no load condition, the frequency of the system at the no load is 50 Hz. Suppose these two are going to supply load demand of 600 megawatt. Then what is the frequency of the system we need to figure out, which is option B, 47.7 Hz is the correct solution of this question. So let's solve this numerical. See, as you can see clearly here, let me assume G1 is the first generator. G1 is the first generator which is having a rating of 200 megawatt with a governor group speed characteristics of 4%, and G2 is having a rating of 400 megawatt with a governor group characteristics of, we can say that it is a governor group characteristics of 5% from no load to full load. See, now I am going to draw a plot, you can see, with respect to frequency and the power. So this is for the plot for the generator 1 and this is for the generator 2. So initially at no load condition, at no load, means whenever the power demand is 0, the frequency of the system is 50 Hz. But whenever the power demand increases, the frequency will fall down. So here, from no load to full load, the full load is 200 megawatt, the full load is 200 megawatt. So at this, it is going to drop off 4%. The frequency is going to drop by 4%. Means drop is 4% means what is the remaining, which is 96%. So 96% is the remaining, which is 96 by 100 into 50 is nothing but 48. So 96 by, so this drop is nothing but 4%. So the remaining is 96%. So 96 by 100 into 50 is nothing but 48. So 48 Hz means at 200 megawatt, the frequency of the system is 48 Hz of the generator 1. Similarly for generator 2, at full load, we can say the governor speed characteristics drop is 5% from no load to full load. So this is the 400 megawatt. So this is now 5%. 5% means the drop is by 5% means the remaining is 95%. So 95 by 100 into 50 is nothing but we are going to get 47.5. So 47.5 we are going to get, which is 95 by 100 into 50 is nothing but 47.5. So this drop is nothing but 5%. So this total drop is 5%. The remaining is nothing but, which is 95%, which is 47.5. So this value is nothing but 47.5 Hz. So 48 for the first one and 47.5 Hz for the second one. So more drop, 5% is merely more drop. More drop means this triangle will be having a large amount of this one. Small drop means here we are going to get it less amount of width here. More drop means we are going to get this one very more width. So this height is very more. If this is the more value, this value will increase further more and more. So now these two generators these two are going to cut in parallel. So they should operate at the same frequency. And also they are going to supply a load demand of 600 megawatt. So let me assume they both should operate at a same frequency. So at a particular F, I am going to draw a straight line, and these two are going to intersect at these two triangles at a point. This is P1 and P2. So P1 is the power which is generated by the G1, and P2 is the power which is generated by the G2. So you can see clearly, now with the help of these things I want to find what is the value of the F. So P1 plus P2 is equal to 600 megawatt, and we have to find what is the value of F. So you can see clearly, now if I see these triangles, so this triangle and this triangle, so this both are same, or you can say slope is same. So therefore for this triangle, what is the slope? Slope is nothing but this by this side, which is 50 minus 48 by 200. And for this triangle the slope is 50 minus F by P1. So we have to equate these two equations, we will get some equation. Similarly for this triangle, so this triangle and this triangle both are in the same slope. So therefore this height is nothing but 50 minus F by P2 is equal to 50 minus 47.5 by 400. So we have to equate these two parts, and we are going to get another equation. So by solving these equations we are going to get the value of F. So what I told you for the generated G1, at full load I already told you F1 is the frequency. So F1 is nothing but 4% drop means the remaining is 96%, which is 100 minus 4 by 100 into no load frequency is 50. So if you solve this one, 96 by 100 into 50 is nothing but 48 hertz. So 48 hertz is the frequency at the full load for the generator 1. So F1 is equal to 48 hertz. Similarly for the generator G2, at full load F2 is the frequency. So it is going to drop by 5%. The remaining is nothing but 95. So 100 minus 5 by 100 into 50 is nothing but 95 by 100 into 50, which is 47.5 hertz. So F2 is the frequency at which we are going to get, at full load we are going to get a frequency of 47.5 hertz. I have already told you for generator 1, I have already told you one important equation, which is 50 minus F by P1 is equal to 50 minus 48 by 200. So if you solve this on the equation, we are going to get P1 is equal to 100 into 50 minus F. Similarly, for the generator G2, I have already told you 50 minus F by P2 is equal to 50 minus 47.5 by 400. So if you solve this one, we are going to get P2 is equal to 50 minus F into 400 by 2.5, which is 160 into 50 minus F. So we know the value of P1 in terms of F, P2 in terms of F. But what is the total demand? 600. So P1 plus P2 is equal to 200. So we know the value of P1, we know the value of P2 in terms of F. And if you substitute here and if you solve this one, we are going to get the value. Only one equation with only one unknown. So now we are going to get the value of F. If you solve it correctly, we are going to get the value of F. So F is equal to 620 by 13. Then we are going to get 47.69, which is nearly equal to 47.7 watts. So this is the frequency of the operation that we are going to get. So whenever the two generators J1 and G2 are connected in parallel, so this is the for load demand of 600, or you can say for load demand of 600 megawatt. So this is the frequency of the operation, which is 47.7 hertz is the correct solution of this question. So now we are going to solve another question. See the question here. The capacitor connected in series with the line is used to. The capacitor connected in series with the line is used to. Option B, it is going to enhance the power system capability, means it is going to increase the power system capability, means it can transfer more amount of power. So therefore, by connecting the capacitor in series with the transmission line, it is going to enhance the power system capability, because whenever they are decreasing the overall reactance of the transmission line, the maximum power that we can send to the transmission line can be increased with the help of keeping the capacitor in series with the transmission line. So option B is the correct solution of this question. So now we'll discuss something more about this one. Due to series capacitance compensation, effective reactance of the transmission line decreases. So power transfer capability of the line increases, because by using the series capacitance compensation, the overall effective reactance of the transmission line decreases. So because of that, the amount of power transfer capability of the line will increase, because the overall power transfer P is equal to V1 into V2 by XL into sin delta. So XC is called as this XL is called as the overall, we can say overall reactance of the line. So because we are going to keep a capacitor, it is having a minus JXC, the overall reactance is going to get decreased. When this overall value will decreases, this overall value will increase. The maximum amount of power transfer can be increased by keeping the series capacitance in the transition line. So you can see clearly as XL decreases, as the overall reactance of the transition line decreases, the maximum power, this is called the maximum power will increase because Pmax is equal to V1 V2 by XL. The maximum power is also called as the steady state limit, means PSSL. It is also called as the steady state limit or the maximum power. So by keeping the capacitance in a series with the transition line, we are going to increase the steady state limit or the maximum power that we can transfer to the line that can be increased, or simply we can say that it is going to enhance the power system capability. So now we are going to solve another question. See the question here. Equal area criteria is a method to determine. See, equal area criteria is a method to determine which one. It is a option A, transient stability. So always we are going to use the equal area criteria is a method by which we are going to determine the transient stability. So now we'll discuss something more about this one. So always the equal area criteria is a method. It is always going to determine the transient stability. So now we'll discuss something more about this one. So we can see clearly here, equal area criteria is a graphical technique which is used to examine the transient stability of the machine system. It is one or more than one with an infinite bus. Here the stability conditions are stated by equating the two areas. So here the stability conditions are stated by equating the two area segments which is present in the power angle diagram. Equal area criteria is used for the transient stability studies. So always the equal area criteria is used for the transient stability studies. If the acceleration area is equal to deceleration area, then the system is stable, otherwise it is unstable. So we can say that equal area criteria is a graphical technique which is used to examine the transient stability of the machine system, which is one or more than one with an infinite bus. Here the stability conditions are stated by equating the two area segments which is present in the power angle diagram. Equal area criteria is used for the transient stability studies. If the acceleration area is equal to deceleration area, then only the system is stable, otherwise it is unstable. So whenever the acceleration area and the deceleration area are equal, then only we can say the system is always said to be stable, otherwise the system is said to be unstable system. So always we are going to use this equal area criteria for studying the transient stability of the system. So therefore equal area criteria is a graphical technique. It is a graphical technique which is used to examine the transient stability of the machine system, which is one or more than one with an infinite bus. Here the stability conditions are stated by equating the two area segments which is present in the power angle diagram. Equal area criteria is used for the transient stability studies, and if the acceleration area is equal to deceleration area, then only we can say the system is said to be stable, otherwise it is unstable. So we can say always we are going to use this equal area criteria. It is basically a graphical technique, and we are going to apply this only for the transient stability of the machine system. Either a machine can be one or more than one with an infinite bus. So basically here we are going to equate the areas of the acceleration area is equal to, if the acceleration area is equal to deceleration area, then only the system is said to be stable, otherwise it is said to be a unstable system. So finally I can say that equal area criteria is a graphical technique which is used to examine the transient stability of the machine system with one or more than one with an infinite bus. Here the stability conditions are stated by equating the two area segments which is present in the power angle diagram. Equal area criteria is used for the transient stability studies. If the acceleration area is equal to deceleration area, then the system is said to be stable, otherwise it is unstable system. So now we are going to solve another question. Two unity feedback systems A and B with open loop transfer functions are G of S is equal to 9 by S into S plus 1 and GB of S is equal to 16 by S into S plus 2. So which of the following statements is correct? So basically they are given two unity feedback systems with open loop transfer functions J of S and GB of S. So by comparing these two systems, we have to find out of this which option is correct. So out of this option A, the system A has the higher overshoot than the system B. So now we'll discuss the exact solution of this question. So option A is the correct solution of this question. So now let us solve this one. You can see clearly here, in this question we are given that, let me assume for the system A. For the system A, what is the transfer function? What is the characteristic equation? Characteristic equation is equal to 1 plus G of S into H of S is equal to 0. In the question they are given both are unity feedback. So H of S is equal to 1 and G of S is equal to 9 by S into S plus 1. So therefore 1 plus 9 by S into S plus 1 is equal to 0. So if we solve this one, we are going to get S into S plus 1 plus 9 is equal to 0. So S square plus S plus 9 is equal to 0. So this is the characteristic equation that we are going to get. So if you are going to compare with the standard characteristic equation which is the second order, s square plus 2 zeta omega ns plus omega n square. So by comparing these two equations, we are going to get omega n square is equal to 9 and 2 zeta omega n is equal to 1. So omega n square is equal to 9, so therefore omega n is equal to 3. 2 zeta omega n is equal to 1. So if we substitute here zeta is omega n is equal to 4, then we are going to get the value of zeta. So zeta is equal to 1 by 2 omega n. Omega n is equal to 3. If you substitute here, we are going to get the damping ratio, or because the damping ratio of the system A is nothing but which is 1 by 6. Then what is the settling time? What is the settling time which is equal to 4 by zeta omega n? This is the settling time for the 2% error. So it is a settling time for the 2% error which is 4 by zeta omega n. So we know the value of zeta, we know the value of omega n. So zeta is equal to 1 by 6 for the system A and omega n is equal to 3. So if we solve this one, we are going to get 8 seconds. So therefore we can say the settling time of the system A is equal to 8 seconds and the damping ratio of the system A is equal to 1 by 6. And the settling time of the settling time of the system A is 8 seconds and the damping ratio of the system A is 1 by 6. Similarly, same thing that we are going to do for the system B also, which is same characteristic equation, which is 1 plus g of s into h of s is equal to 0. So h of s is equal to 1 and gb of s is equal to 16 by s into s plus 2. So if we solve this equation, we are going to get s into s plus 2 plus 16 is equal to 0. So s square plus 2s plus 16 is equal to 0. So if you are going to compare with the standard second order characteristic equation, which is s square plus 2 zeta omega ns plus omega n square is equal to 0. So by comparing these two equations, we are going to get omega n square is equal to 16 and 2 zeta omega n is equal to 2. Omega n square is equal to 16 means omega n is equal to 4 and 2 zeta omega n is equal to 2. So 2 cancels. Zeta is equal to 1 by omega n. Omega n is equal to 4. So therefore the damping ratio of the system B is equal to 1 by 4. Then what is the settling time for 2% error for system B, which is 4 by zeta omega n? The zeta value is 1 by 4 and omega n is equal to 4. So you are going to get 4 seconds. So the damping ratio of system B is 1 by 4 and the settling time for the system B is 4 seconds. So now we can see clearly that I have already told you the damping ratio of system A is nothing but which is 1 by 6. The damping ratio of the system A is nothing but which is equal to 1 by 6 and the damping ratio of the system B is equal to 1 by 4. The damping ratio of the system A is equal to 1 by 6 and the damping ratio of the system B is equal to 1 by 4. So simply we can say that the damping ratio of system A is always lesser than the damping ratio of the system B. And now if you see the settling time, so what is the settling time? The settling time of system A is equal to 8 seconds and the settling time of the system B is equal to 4 seconds. So simply we can say that the settling time of the system A is always higher when compared to settling time of system B. So therefore simply we can say that finally we can say that whenever the damping ratio increases, the peak overshoot decreases because MP is equal to e to the power of minus zeta pi by under root over 1 minus zeta square. As zeta increases, the peak overshoot value will decrease. Similarly, settling time is equal to 4 by zeta omega n. As zeta increases, the settling time decreases. So therefore finally we can say that as the damping ratio increases, then the peak overshoot decreases and the settling time also decreases. So finally I have already told you the damping ratio of the system B is always greater than the damping ratio of the system A. So we can say that the damping ratio of system B is nothing but 1 by 4 and the damping ratio of system A is 1 by 6. So therefore simply we can say that the damping ratio of system B is always greater than the damping ratio of system A. So as the damping ratio increases, then what is the peak overshoot? Peak overshoot value will decrease. So therefore the peak overshoot of system B is lesser than the peak overshoot of system A. So as the damping ratio increases, the peak overshoot will decrease. So therefore as the system damping ratio is higher than system damping ratio A, so therefore simply we can say that the peak overshoot of system B is lesser than the peak overshoot of system A. And also we have seen that the settling time of system A is 8 seconds and the settling time of system B is 4 seconds. So from this we can see clearly that the settling time of system is always greater than the settling time of system B. So finally I can say that whenever the damping ratio increases, the peak overshoot decreases and the settling time is also decreases. So finally I can say that the peak overshoot of the system B is always lesser than peak overshoot of system A, and also the damping ratio of system B is always greater than damping ratio of system A, and the settling time of system A is always greater than the settling time of system B. Therefore we can conclude that system A has the higher overshoot when compared to system B. So system A is having a higher overshoot when compared to system B because it is having a low damping ratio. So low damping ratio means higher peak overshoot. As the damping ratio increases, peak overshoot decreases and the settling time decreases. So now we are going to solve another question. The gain margin of the system G of S is equal to 1 by S into S plus 1 into S plus 2 is given by. So we have to find what is the gain margin of this system, which is G of S is equal to 1 by S into S plus 1 into S plus 2. We need to figure out. So what is 4 options? Option D. 6 is the correct solution of this question. So let's solve this numerical. So G of S is equal to 1 by S into S plus 1 into S plus 2. So what is the gain margin? Gain margin is equal to 1 by mod of G of S into H of S at omega PC. So PC is called the phase crossover frequency. So PC is called the phase crossover frequency. So this is the frequency at which the phase angle of G of S H of S is equal to minus 180 degree. So gain margin is equal to 1 by mod of G of S into H of S at omega PC. So what is the value of G of S H of S? Let me assume H of S is equal to 1. So G of S into H of S is equal to 1 by S into S plus 1 into S plus 2. So now in place of S I am going to replace S by J omega. Then I am going to get 1 by J omega into J omega plus 1 into J omega plus 2. So this is called as the rectangular format. Now I want to convert into polar format, which is 1 by omega into 1 plus omega square into 2 square plus omega square at an angle of minus 90 minus tan inverse omega minus tan inverse of 2 by say omega by 2. So at an angle of minus 90 minus tan inverse omega minus tan inverse omega by 2. So this is the phase angle that you are going to get. So this is the polar format. So the magnitudes are multiplied and the phase angles are added. If it goes upper part, it is going to become negative. So this is the phase angle. But first we have to find what is the phase crossover frequency. Phase crossover frequency means here the angle part should be always equal to minus 180 degree. So at that frequency is called as the phase crossover frequency. So phase angle of G of S H of S at omega PC is equal to minus 180 degree. So you have to equate this part to minus 180. So therefore minus 90 minus tan inverse of omega minus tan inverse of omega by 2 is equal to minus 180. So if you solve this one, this is basically omega PC. This is the frequency at which the phase angle is called minus 180. So if you solve this one, we are going to get like this, which is tan inverse omega plus tan inverse omega by 2 is equal to 90 degree. So what is the value of tan theta plus tan of theta 1 plus theta 2 is equal to tan theta 1 plus tan theta 2 by 1 minus tan theta 1 into tan theta 2. So if you apply tan on both sides, then we are going to get like this, which is omega plus omega by 2 by 1 minus omega into omega by 2 is equal to tan 90 is nothing but tan 90 is equal to infinity because tan of, so this is basically theta. So tan of tan inverse of theta is nothing but theta. Tan of tan inverse of theta is equal to again theta. So now if you solve this one, infinity is nothing but 1 by 0. So this denominator should be always equal to 0. So therefore tan of tan inverse theta is equal to theta. So therefore this denominator should be equal to 0. So therefore 1 minus omega square is equal to 0. So 1 is equal to omega square by 2. So omega square is equal to 2. So omega is equal to root 2. So this is the omega PC. So this is the omega PC at which we are going to get the phase angle is equal to minus 180 degree. So this is the phase angle. So this is the phase crossover frequency. At this frequency only we are going to get the minus 180 degree. So now we know this one. Now we have to find what is the magnitude of the G of S H of S at omega PC. So now I have already told you the magnitude of G of S H of S just now we have shown, which is the in the polar format that we have already done that. So I have already told you in the polar format just now we have seen, which is 1 by omega into under root over 1 plus omega square into under root over, and we can say simply which is, so I already told you bar of G of S H of S is nothing but just now we have seen, which is 1 by omega into under root over 1 plus omega square into under root over 4 plus omega square. In place of omega, substitute this root 2. So then we are going to get 1 by root 2 into under root over 1 plus root 2 whole square into under root over 4 plus root 2 whole square. So if we solve this one, we are going to get 1 by root 2 into root 3 into root 6. So therefore the G of S H of S at the magnitude part omega PC is equal to 1 by root 6 is equal to 1 by 6. Then what is the gain margin? Gain margin is equal to 1 by mod of G of S H of S at omega PC. So you have to keep this one here. So 1 by 6 is equal to 6. So therefore the gain margin is equal to 6. So gain margin formula is equal to basically the gain margin formula is nothing but which is equal to the gain margin is equal to 1 by mod of g of s h of s at omega pc. So omega pc means it is a phase angle of g of s h of s at omega pc, it is equal to minus 180 degree. So like this we are going to solve this question. So the answer is 6. The gear mass is equal to 6 is the correct solution of this question. Now we are going to solve this question. See the question here. The transfer function t of s is equal to y of s by v of s is equal to 1 by s cube plus 3s square plus 2s plus 10 is represented in the state variable form. In the system matrix A is given by. So we have to find what is the system matrix A we need to figure out. So out of these 4 options, option C is the correct solution of this question. So this is the system matrix. So now we'll solve the solution. So now you can see clearly here we are going to solve this question. Listen carefully. We are figuring out the system model from differential equation of the transfer function. So we are figuring out the system model from the differential equation of the transfer function. See, output itself is taken as one of the state variable. So here in this, output itself is taken as one of the state variable, and the number of state variables are always equal to order of the system. So the number of state variables are always equal to the order of the system. So when figuring out the system model from differential equation or transfer function, always the output itself is taken as one of the state variable, and the number of state variables are always equal to the order of the system. In the matrix A, is said to be in the Bush or the companion form or controllable canonical form. So then the matrix A is said to be basically Bush or the companion form or the controllable canonical form. So whatever the matrix A that you are going to get, it is said to be in the Bush form or the companion form or the controllable canonical form. Then what is the value of y of s by u of s? Let me take a small examples to explain the concept. Then y of s by u of s is equal to as plus b by s square plus ps plus q. Suppose in this format is there. Suppose if any transfer function y of s by u of s, if it is there in this format, which is y of s by u of s is equal to as plus b by s square plus ps plus q, then what we have to do basically very simple, which is let me do into split into this fashion, which is 1 by s square plus ps plus q into as plus b. So 1 by s square plus ps plus q into as plus b. So you can see clearly one important point that you can easily observe here, which is here now we are going to see the order is the second order. The second order means we can represent in terms of the second order means the order of the system is equal to number of state variables. So here it is a second order. So the number of state variables are 2. So x1 dash and x2 dash, which is x dot is equal to ax plus b and y is equal to cx plus d. So x dot is equal to ax plus b. So 2 state variables x1 dot x2 dot, here a, and this is x1 x2, this is b and this is u. So how to write this one? So you have to go in this direction. In this direction you have to go like this. Here you have to go in this manner, and here also you have to go in this manner, and this one you have to dot here. You have to keep a circle. So if you are going in this format, then always you have to, in the answers writing, you have to go in the opposite direction. Like this, if you are going here, you have to go in this direction, which is the first thing you have to go. You have to write it in negative fashion, which is minus q minus p, minus q minus p. As it is a second order, the order of the matrix is also 2 by 2. So minus q minus p. Then always the upper number is always 1, and then it is 0. Then whatever this number is there, just keep this number, same number here. So 0, 1. And here now you are going in this fashion, right? Same thing you have to go here, which is same numbers you have to write. You don't have to deviate anything. So same write of each and everything. So BA. So this is the word that you are going to get here, which is, you can see clearly this is y is equal to BA x1 x2. So this is the matrix A for this equation, for this transfer function. This is the matrix A that you are going to get for the second order. Suppose if I go for the third order, then we will see what is going to happen, which is y of s by u of s is equal to a square plus bs plus c by s cube plus p square plus qs plus r. Then what is you are going to get? Listen carefully. Then y of s by u of s is equal to, then y of s by u of s is equal to, same fashion we are going to split into 2 parts, 1 by s cube plus p square plus qs plus r into a square plus bs plus c. I have already told you the order of the system is equal to the number of state variables is equal to order of the system. As the order of the system is 3, so we need 3 state variables, x1 dot, x2 dot and x3 dot. Here x dot is equal to ax plus b. So a, x, x1 is to x3 plus bu. So this is b and this is u. So y is equal to cx plus d. See clearly here, I've already told you have to go in this direction. You have to go in this direction. While writing, you have to go in this direction. So therefore here, the first letter is R. So you keep your negative values. Minus R, minus Q, minus P. It's a 3 by 3 matrix. So the upper number is always 1. Then 0. Again go 1 here. Then carefully you have to write in this one. Minus R, minus Q and minus P. The upper is always 1. And then what you have to do basically here, very simple. Then you keep it here 0 and then write 1. Or simply you can also write in another fashion. Keep it here 1 and then go upper and then keep it here 1. Then go upper 0. Again go for left, it is 1 again. Again you go upper and then go left side, you are going to keep 1. So like this you have to always go for this one. So therefore here minus R, minus Q, minus P, go upper 1 and then go upper 0, again go slightly here to the left side, you are going to keep here 1 and then go upper and then keep here 1, again go upper, again go left and keep here 1. So like this you have to write this one. This is called as the companion or the bush form. So the whatever the matrix that you are going to get, it is called as the bush form or the companion form or the controllable canonical form. So like this you are going to get. So therefore now, so whatever the one you are is there, you have to keep it here. Same one you have to keep it here. So 0, 0, 1. And then what is the value of C? C is very simple. Whatever these values are, they just write same thing. CBA. So CBA. So like this you are going to get. So this is the way that you always have to write in this fashion. So this is the matrix A for this transfer function. Suppose in the example they are given a transfer function P of s is equal to y of s by u of s is equal to 1 by s cube plus 3s square plus 2s plus 10. So for this we have to write the matrix A. I've already told you have to go in this direction. While writing you have to go in this opposite direction, which is minus 10, minus 2 and minus 3. I've already told you the upper is always 1 and then go upper and go to the left, keep it 1. Again go upper 0, again go left, keep it 1. So like this you have to follow, like a stepwise. Then whatever the matrix that you are going to get, it is called as the system matrix or matrix A. This matrix is also called as a bush form or the companion form. So this is the way that you always have to figure out. This is the way that you always have to follow in order to figure out the system model or the transfer function from the differential equation, or you can say figuring out the system model from the differential equation or the transfer function. So output itself is taken as one of the state variable and the number of state variables are always equal to the order of the system. And whatever the matrix that you are going to get, it is said to be a bush form or the companion form or the controllable canonical form. So now we are going to solve another question. See the question here. Consider the following statements with respect to time and frequency response of a second order system. The statement 1 is peak overshoot is indicative of the damping in the system. Second statement is resonance peak depends on the damping and the natural frequency. Statement 3 is the resonance frequency depends only on the damping in the system. And statement 4 is the resonance peak and the resonance frequency can be used as the performance measures in the design of the control system. The correct statements are only option A. Only first and the fourth statements are the correct, but not the second and third. So in the question they are basically saying that consider the following statements with respect to time and frequency response of a second order system. Statement 1 is peak overshoot is indicative of the damping of the system. Peak overshoot is the indicative of the damping in the system. Statement 2, the resonance peak depends on the damping and the natural frequency. And the statement 3, the resonance frequency depends only on the damping in the system. And the statement 4, the resonance peak and the resonance frequency can be used as a performance measures in the design of control system. The correct statements are only option A, which is statement 1 and statement 4 are true, but the statement 2 and statement 3 are wrong. So you can see clearly here. Here MR is called as a resonance peak. See, MR is called as a resonance peak. MR is called as a resonance peak. Its value is equal to 1 by 2 zeta on the root over 1 minus zeta square. So resonance peak is nothing but MR is equal to 1 by 2 zeta on the root over 1 minus zeta square. Now, what is the MP? MP is called as a peak overshoot. Peak overshoot is nothing but e to the power of minus zeta pi by under root over 1 minus zeta square. Then what is the resonance frequency? Omega r is called as a resonance frequency, which is omega r is called as a resonance frequency is equal to omega n into under root over 1 minus 2 zeta square. So we can say clearly very important point, which is MR is called as a resonant peak. It is equal to 1 by 2 zeta under root over 1 minus zeta square, and MP is called as a peak overshoot is equal to the power of minus zeta pi by under root over 1 minus zeta square, and omega r is called as a resonant frequency is equal to omega n into under root over 1 minus 2 zeta square. So these are the very three important formulas that you always have to understand. MR is called as a resonant peak is equal to 1 by 2 zeta under root over 1 minus zeta square, and MP is called as a peak overshoot. MP is called as the peak overshoot. Its value is equal to the power of minus zeta pi by under root over 1 minus zeta square, and omega r is called as a resonant frequency is equal to omega n into under root over 1 minus 2 zeta square. So these are the three very important formulas, because definitely questions have been asked on these formulas. So I recommend you to remember these three formulas, which is MR is called as a resonant peak, which is 1 by 2 zeta under root over 1 minus zeta square, and MP is called as a peak overshoot is equal to, which is e to the power of minus zeta pi by 1 minus e to the power of minus zeta pi by under root over 1 minus zeta square, and omega r is called as a resonant frequency is equal to omega n into under root over 1 minus 2 zeta square. See, at this resonant frequency, whatever the magnitude that we are going to get, it is called as a resonant peak. So whatever at resonant frequency, at this resonant frequency, whatever the magnitude that you are going to get, it is called as a resonant peak. So now in the statement 1, they are given that the statement 1 is the peak overshoot is the indicator of the damping in the system. Yes, peak overshoot is going to give you the damping of the system. Yes, the statement 1 is correct. The statement 2, the resonant peak depends on the damping and the natural frequency. The resonant peak is depending only on the damping ratio but not on the natural frequency. So we have to say that the resonant peak is depending only on the damping but not on the natural frequency. So in the statement 2 they are given wrong, because they are given that it is depending on both the damping ratio and also natural frequency. But if you see clearly, it is depending only on the damping ratio but it is independent of natural frequency. So statement 2 is wrong. In the statement 3, they are given that the resonant frequency depends only on the damping in the system. See, you can see clearly, but the resonant frequency is depending on the damping ratio and also the natural frequency. So statement 3 is also wrong. In the statement 4, they are given that the resonance peak and the resonant frequency can be used as a performance measures in the design of control system. Yes, whatever the resonant peak and the resonant frequency, these both are very much useful in designing the control system. So always the resonance peak and the resonant frequency can be used as a performance measures in the design of control system. So finally I can say that here peak overshoot is the indicator of the damping of the system, because if you know the peak overshoot, then you can easily find the damping of the system. See, as the damping ratio increases, the peak overshoot decreases and the setting time decreases. I have already told you, whenever the damping ratio increases, the peak overshoot decreases and the setting time will decrease. And always the resonant peak is only depending on the damping ratio only. The resonant peak is depending only on the damping ratio, whereas the resonant frequency is depending on both the damping ratio and also on the natural frequency. The resonant frequency is depending on both the damping and also the natural frequency. And the resonant peak and the resonant frequency can be used. It means MR and the omega R. So MR and the omega R called as the resonant peak and the resonant frequency both can be used as a performance measures in the design of the control system. So finally I can say that MR is called as a resonant peak is equal to 1 by 2 zeta under root over 1 minus zeta square, and MP is called as a peak overshoot is equal to the power of minus zeta pi by under root over 1 minus zeta square, and omega R is called as a resonant frequency is equal to omega n into under root over 1 minus 2 zeta square. So these three are very much useful formulas, because always questions have been asked on this formula. So therefore MR is called as a resonant peak is equal to 1 by 2 zeta under root over 1 minus zeta square, and MP is called as a peak overshoot is equal to e to the power of minus zeta pi by under root over 1 minus zeta square, and omega R is called as a resonant frequency is equal to omega n into under root over 1 minus 2 zeta square. So now we are going to solve another question. See the question here. Consider the following statements regarding a root locus of a system. Statement 1. Breakaway points always occur on the negative real axis. Option B. Statement B. A point on the real axis lies on the root locus if the total number of real poles and the zeros to the right of the point is even. Statement 3. The number of branches of root locus going to infinity is equal to the difference between the number of open loop poles and zeros. Statement 4. The value of k on the root locus can be determined by using only the magnitude criteria. So which of the statements are not correct? So out of these 4 statements, which statements are not correct we need to figure out. So out of these 4 options, option C is the correct solution of this question. Statement 1 and statement 2 are always incorrect because always the breakaway point can occur at any point on the S-plane. Because the breakaway point can occur at any point on the S-plane, and statement 2, which is the correct statement, is always a point on the real axis lies on the root locus if the total number of real poles and zeros to the right of that point should be always odd number but not even, and the number of branches of the root locus going to the infinity is equal to the difference between the number of open loop poles and the zeros, which is the magnitude of the p minus z. And the last one is the value of k on the root locus can be determined by using only the magnitude criteria. So therefore these are the 4 statements which are always correct, but here the first 2 statements are always wrong because always the breakaway point can occur at any point on the S-plane, and always a point on the real axis is said to be a part of the root locus if the total summation of the real poles and the zeros to the right side of that point is always odd number, then only we can say it is on the root locus. That point is on the root locus. And the number of branches of root locus going to infinity is always equal to the difference between the number of open loop poles and the open loop zeros. The magnitude of p minus z is going to tell you the number of branches which are going to infinity. The value of k on the root locus can be determined only with the help of magnitude criteria only. So option C, 1 and 2 are the wrong statements. So now you can see clearly breakaway point. So breakaway point can occur at any point in the S-plane. So breakaway point can occur at any point on the S-plane. So basically, breakaway point can occur at any point on the S-plane. It is not necessary only to occur at the negative real axis. It can occur at any point in the S-plane. So breakaway and break-in can occur at any point in the S-plane. So breakaway point can occur at any point in the S-plane. A point on the real axis lies on the root locus if the total number of real poles and the zeros to the right of the point is always odd. So whenever a point on real axis is said to be on the root locus if the total number of real poles and zeros to the right side of the point is odd. So whenever the sum of open loop poles and the zeros, the real poles and zeros to the right side, if it is odd, then only that point is going to lie on the root locus. A point on the real axis lies on the root locus if the total number of real poles and the zeros to the right of the point is odd. The number of branches of the root locus going to infinity is equal to the difference between the number of open loop poles and zeros, which is mod of p minus z. So the number of root locus branches which are going to infinity, it is equal to the difference between the number of open loop poles and the open loop zeros. So therefore we can say that the difference of the number of open loop poles and number of open loop zeros, that is number is going to tell you the number of branches of root locus which are going to infinity. And the value of k on the root locus can be easily determined by only the magnitude criteria. So with the help of magnitude criteria only, you can figure out the value of k on the root locus can be easily find out with the help of magnitude criteria. So finally we can say that in the question they have given statement 1 wrong, statement 2 wrong, and the statement 3 is correct and the statement 4 is correct. So therefore in the question they asked about which statements are not correct, so which are 1 and 2. So 1 and 2 are the wrong statements because in the question they have asked which statements are wrong. So 1 and 2 are the wrong statements. So now we are going to solve this question. See the question here. The asymptotic Bode plot of a system G of S is shown in the figure. So they have basically given a asymptotic Bode plot of a system G of S. They have shown in the figure. You can see clearly this line has a slope of minus 20 decibels per decade, and this line has a slope of 0 decibels per decade, and this line has a slope of minus 20 decibels per decade, and this line has a slope of minus 40 decibels per decade. So this is a point at omega is equal to, this omega is equal to 10, and this is omega is equal to 100. So this is the 4 dB. So based on this, we have to find what is the transfer function of the system G of S we need to figure out. So all these 4 options, option C is the correct solution of this question. So if you see clearly, the initial slope is minus 20 means there is a 1 0 or we can say 1 pole at the origin. Here we are going to add plus we are going to add here, we are going to add at this point plus 20 means we have to add a 0 here. Similarly here we have to add minus 20. So therefore simply we are minus 20 means we have to add a pole of 1. Similarly here we have to add again minus 20. So here also we have to add a pole. So this is the way that we are going to analyze this question. So option C is the correct solution of this question. So let's solve this numerical. As you can see clearly, this line is minus 20 decibels per decade. This is 0 decibels per decade, and this is minus 20 decibels per decade, and this is minus 40 decibels per decade. So I've already told you here you have to add plus 20, then only you are going to get 0. Minus 20 plus 20 is nothing but 0. So we have to add here plus 20. So this plus 20 is nothing but we have to add a 0 at omega is equal to 2. Similarly, here again 0 minus 20 is nothing but minus 20. So here we have to add a minus 20 here. So it is basically a slope. It is a pole. It is a pole of at omega is equal to 10. Similarly here again you have to add minus 20 because minus 20 plus minus 20 is equal to minus 40. So therefore here we have to add a pole of slope minus 20 decibels per decade at omega is equal to 100. Then what is the initial slope? Initial slope is nothing but I have already told you the initial slope is equal to minus 20 decibels per decade. So therefore one pole at the origin which is 1 by s. Then I have already told you at omega is equal to 2. At omega is equal to 2 we have to add a pole of slope minus 20. So therefore we have to add a, listen carefully, at omega is equal to 2, at omega is equal to 2 we have to add a 0. At omega is equal to 2 we have to add a 0 because we are adding plus 20. So therefore we have to add a 0. So here omega 1 is equal to 2. Then what is T1? T1 is equal to 1 by omega 1 which is 1 by 2. Similarly at omega is equal to 10. At omega is equal to 10 we are adding minus 20. So therefore we are adding a pole. So therefore here omega 2 is equal to 10. Then what is T2? T2 is 1 by omega 2 which is 1 by 10. Similarly at omega 3 is equal to 100. At 100 we are adding minus 20. So minus 20 is nothing but pole. So omega 3 is equal to 100 means what is T3? T3 is equal to 1 by omega 3 is equal to 1 by 100. So now we are going for the open transfer function g of s h of s which is the standard format. This is called as the standard format, or you can say the standard form of writing the transfer function which is k into, see we are having 1 0 2 poles and 1 pole at origin. So listen carefully, 1 pole at origin, 1 0 and 2 poles of single order. So therefore k into 1 plus st1 by s into 1 plus st2 into 1 plus st3. So this is a 0, this is a single pole, this is a single pole, and this is a pole at origin, and this is a k. So g of h of s is equal to k into 1 plus st1 by s into 1 plus st2 into 1 plus st3. This is going to tell you 1 0, this is going to tell you 1 pole, this is going to tell you 1 pole at one order, at first order. So therefore now you know value of t1, t2 and t3. You have to substitute here, and if you are going to get in this format. So this is the g of s h of s in standard. This is called a time constant format. So this is what that you are going to get. So now we have to know what is the value of k. So if you want to know what is the value of k, you have to write the equation for the initial line. So you have to write the equation for the initial line which is y is equal to ms plus c. C is always equal to 20 log k. For the initial line in the Bode plot, you always have to write the equation y is equal to mx plus c. Then y is equal to ms plus c is always equal to 20 log k. Yeah, and you can see clearly what is x. X is nothing but in a Bode plot what is the value of x? X is equal to log omega. So therefore in place of x I am keeping here it is log omega. And what is the initial line slope? Initial line slope is nothing but minus 20. So here you have to keep here minus 20. So therefore y is equal to minus 20 log omega plus 20 log k. See, I have already told you from the figure at omega is equal to 2 we are going to get 4 dB. You can see clearly at omega is equal to 2 we are going to get 4 dB. So I am going to keep this point at omega is equal to 2, I want 4 dB. In place of omega, keep omega is equal to 2 and then y is nothing but 4. So if you solve this one, we are going to get 4 is equal to minus 20 log 2 plus 20 log k. So only one equation with only one unknown. So we can easily get the value of k, which is 4 plus 20 log 2 is equal to 20 log k. So therefore 4 plus 20 log 2 by 20 is nothing but log k. So k is equal to, because always these are base 10, so take here power So 10 to the power of 4 plus 20 log 2 by 20. So if you solve this one, we are going to get this value as this value as 0.5. So k is equal to 10 to the power of 0.5, which is equal to 0.5 is equal to 1 by 2 means root of 10. Root of 10 is nearly equal to 3.16. So root of 10 is nearly equal to 3.16. So always remember log 2 base 10 is nothing but 0.301. So log 2 base 10 is equal to 0.301. So always remember that log 2 base 10 is equal to 0.301. So log 2 base 10 is always equal to 0.301. So now you know the value of k, substitute here in the standard time constant standard form. So therefore this is called as the standard time constant format, which is k is equal to 3.16 into, now do a simplification of this one, and if you do a simplification correctly, finally we are going to get the solution, which is g of s h of s is equal to 1580 into s plus 2 by s plus 10 into s plus 100. So this is the correct solution of this question. So g of s h of s is equal to 1580 into s plus 2 by s plus 10 into s plus 100. So you have to do a simplification very carefully because k is equal to 3.16. So take 2 LCM, 2 plus s by 2 into s into 10 plus s by 10 into 100 plus s by 100. So if you do this one, 3.16 into s plus 2 into, here 10 goes upward, 10 into 100 by s into s plus 10 into s plus 100. So therefore now 10 into 100 is nothing but 1000. So 1000 by 3.16 and 1000 by 2 into s plus 2 by s plus 10 into s plus 100. So 2 ones are 2 500s are. So 2 5s are 10, 0 0, 500. So 3.16 into 500 is nothing but 1580 into s plus 2 by s plus 10 into s plus 100. So this is the open loop transfer function of this body plot diagram. So now we are going to solve another question. See the question here. The rise time Tr in BJT is defined as the time during which collector current rises from. So in this question basically they are asking that what is the rise time in BJT. So what is the time for which the collector, based on the collector current we need to find what is the rise time. It is the time for which the collector current rises from 0.1 ICS to 0.9 ICS, where ICS is called as the saturated, or you can say the collector current. So saturation of collector current. So therefore the rise time in BJT it is defined as the time during which the collector current rises from 0.1 ICS to 0.9 ICS, where ICS is called as the peak value of the collector current or saturated collector current. So now we'll discuss something more about this one. So you can see clearly the definition of rise time Tr in BJT. The definition of rise time Tr in BJT is the time required for the collector current in a BJT to rise from 10% of its maximum saturated ICS current to 90% of its maximum saturated ICS current, that is from 0.1 ICS to 0.9 ICS. So you can see clearly from this graph, it is a graph between the collector current with respect to time. So you can see this is called as the 10% of ICS means 0.1 ICS. This is 90% of ICS means 0.9 ICS. So whatever the time required for the collector current to go from 10% of ICS to 90% of the ICS, it is called as the rise time. So this time is called as the rise time. So therefore the time required for the collector current in a BJT to rise from 10% of its maximum saturated ICS current to 90% of its maximum saturated ICS current, that is from 0.1 ICS to 0.9 ICS, it is called as the rise time. So therefore we can say the definition of rise time Tr in BJT is very simple. The time required for the collector current in a BJT to rise from 10% of its maximum saturated ICS current to the 90% of its maximum saturated ICS current, that is from 0.1 ICS to 0.9 ICS. So 10% means 0.1 ICS, 90% of ICS means 0.9 ICS. So whatever the time required for the collector current to go from 0.1 ICS to 0.9 ICS, it is called as the rise time. ICS is the peak value of the collector current or saturated collector current. Now we are going to solve another question. See the question here. The convolution of two sequences shown in the figure is the sequence. So we have to find what is the convolution of these two sequences. See, at x is equal to 0, it has 2. For x is equal to 1, it has 1. At x is equal to 2, it has minus 2. Similarly here, for this x2 of n, at 0, it has 0. For 1, it has 1. For 2, it has minus 2. So this is the sequence. Now we have to do what is the combination of these two signals. So these 4 options, all the options are wrong. So now we'll discuss the exact solution of this question. So I already told you x1 of n. So x1 of n is nothing but here at x is equal to 0, I already told you it is 2. At x is equal to 1, its value is 1. At x is equal to 2, its value is minus 2. So we can write with this format, which is 2, 1 and minus 2. This arrow indicates that at x is equal to 0, its value is 2. So this is to the RHS side. So at x2 of n, we have already told you for x2 of n, at 0 its value is 0. For 1 its value is 1. For 2 its value is minus 2. So therefore, this arrow indicates that at x is equal to 0, we are going to keep this value and this is the right sequence, the right side values. So no answer, all options are wrong. So all options are wrong. So now we'll discuss the exact solution. So convolution of these two signals means x1 of n, convolution of x2 of n. So we can write in the delta fashion, which is 2 into delta of n plus delta of n minus 1 plus minus 2 into delta of n minus 2. Convolution of 0 into delta of n plus delta of 1 into delta of n minus 1 plus minus 2 into delta of n minus 2. So if you do the convolution of these two signals like multiplication, so this into this, again 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 this into this. So you have to do like this one by using the property which is delta of n minus a convolution of delta of n minus b is equal to delta of n minus of a plus b. So this is the formula that you always have to use in order to make the simplification. So delta of n minus a convolution of delta of n minus b is equal to delta of n minus of a plus b. So delta of n minus a convolution of delta of n minus b is equal to delta of n minus of a plus b. So this is the property that you have to use in order to simplify this one. So finally you are going to get in this format. If you do simplification, we are going to get which is 2 into delta of n minus 1 minus 4 into delta of n minus 2 plus delta of n minus 2 minus 2 delta of n minus 3 minus 2 delta of n minus 3 plus 4 delta of n minus 4. If we further simplify, finally we are going to get 2 into delta of n minus 1 minus 3 into delta of n minus 2 plus minus 4 into delta of n minus 3 plus 4 into delta of n minus 4. So what is the sequence now? 0, 2, minus 3, minus 4, 4. So this is the overall convolution of the signal, the overall signal that you are going to get. This is a convolution, but this is not present in any of the options. So this is the correct solution of this question. So you have to use this principle, which is delta of n minus a convolution of delta of n minus b is equal to delta of n minus of a plus b. So this is the principle that you have to use in order to simplify this one. So now we are going to solve this question. See the question here. So you can say clearly, consider the discrete system. So consider the discrete system y of n is equal to a1 into x of n minus 1 plus a2 into x of n plus a3 into x of n plus 1. Then what is the system is? So they are given a discrete system, output is y of n and input is x of n, and the input-output relation they are given for a discrete time system. So now we have to find what is the type of the system. So the four options, option C, linear and the non-causal is the correct solution of this question. As you can see clearly in this question, we can say that. So as you can see clearly that consider the discrete system y of n is equal to a1 into x of n minus 1 plus a2 into x of n plus a3 into x of n plus 1. So basically in this question, we have to find what is the type of the system. So regarding the linear property and the causal property, as you can see clearly, this equation has no nonlinear terms. All are the linear terms in terms of x. In terms of x only, there is nothing like x square is cube or x square root. There is nothing like square roots like that. So only linear terms are there. So definitely the system will be always linear. And now you can see, suppose if you keep n is equal to 0, if you keep n is equal to 0, then y of 0 is equal to a1 into x of minus 1 plus a2 into x of 0 plus a3 into x of 1. As you can see clearly, whenever the output we need at t is equal to 0, but input we are going to get at x is equal to 1. So therefore, the present output is depending upon the future input. So we can say it is said to be a non-causal system. So option C, the system is basically linear system and also non-causal system. So now we will discuss something more about this one. So now you can say clearly here, y of n is equal to, so y of n is equal to a1 into x of n minus 1 plus a2 into x of n plus a3 into x of n plus 1. As you can see clearly, this is the equation they are given, which is y of n is equal to a1 into x of n minus 1 plus a2 into x of n plus a3 into x of n plus 1. So now, as the equation doesn't have any nonlinear term, so it satisfies both derivative and also homogeneity, hence it is said to be a linear system. See, if any system wants to satisfy linearity, then it has to satisfy two conditions. One is called as the homogeneity principle and the other is called as the superposition principle or additive principle. If these two principles are satisfied, then we can say that system is said to be linear system. So for a system to be linear, it has to satisfy two conditions. One is the superposition theorem or I2 and the other is called as the homogeneity. So if these two theorems are satisfied, then we can say that the system is said to be a linear system. As you can see clearly, this equation is not having any nonlinear terms, all are linear terms. So by seeing only we can say the system is said to be a linear system. So as the equation doesn't have any nonlinear terms, so it satisfies both the additive or superposition and the homogeneity principles. So definitely it is said to be a linear system. So now suppose I want to check the causality property. So now I want to find what is the output at n is equal to 0. So if I substitute n is equal to 0, then y of 0 is equal to in place of n I am going to substitute n is equal to 0. Then I am going to get a1 into x of minus 1 plus a2 into x of 0 plus a3 into x of 1. As you can see clearly, the present output is depending upon the future input. At t is equal to 0, the input is depending upon future input x of 1. So present output is depending upon the future input. So and here it is the past input and the present input, and this is the future input. So you can see clearly this present output is depending upon the past input, present input and future input. So if the system is depending on the future input, then it is said to be non-causal system. Otherwise it is said to be a causal system. So if the present output is depending upon the future input, then the system is said to be a non-causal system. Otherwise it is said to be a causal system. So at t is equal to 0, the output is depending upon the future input, that is at t is equal to 1. So it is said to be a non-causal system. So finally I can say that the system is said to be a non-linear and also it is said to be, the system is said to be a linear system and also it is a non-causal system. So now we are going to solve another question. See the question here. If f of t and f of omega are the Fourier transform pairs, then consider the following statements. Statement 1. F of omega exists if f of t has finite energy. Statement 2. The knot of the f of omega is an odd function. Statement 3. F of t minus t transforms to f of omega into e to the power of j omega t. Statement 4. F of t into e to the power of j omega t transforms to f of omega minus omega naught. So which of these statements are correct? So they are given 4 statements. Where f of t is the time domain expression and f of omega is the Fourier transform of the f of t. So they are given the 4 statements. Out of these, which are the correct statements for them to find. So statement 1 and statement 4 are the correct, but the statement 2 and statement 3 are wrong. So option C is the correct solution of this question. So let me discuss something. Always see f of omega is going to exist if f of t has a finite energy. Yes, it is always true. See, whenever the f of t has a finite energy, then only the f of omega is going to get exist. Whereas the magnitude of f of omega is always an even function, whereas the phase angle of f of omega is an odd function. Similarly here, f of t minus t. So what I told you, the Laplace transform of f of t minus t is equal to e to the power of minus ts into f of s. Here e to the power of minus st. S is equal to j omega. So e to the power of minus j omega t. So here it has to be e to the power of minus j omega t. But they are given plus here, so it is wrong. So always f of t minus t has a Fourier transform e to the power of minus j omega t into f of omega. So here they are given positive, so the statement is wrong. But for the first statement, yes, it is always true. The Fourier transform of, or we can say, the Fourier transform of f of t into e to the power of j omega t, omega naught t is nothing but which is f of omega minus omega naught. So Fourier transform of f of t into e to the power of j omega naught t is nothing but which is f of omega minus omega naught. So statement 4 is also correct. So now we'll discuss something more about this one. As I already told you, statement 1 is correct, statement 2 is wrong, statement 3 is also wrong, and statement 4 is correct. So now we'll discuss each one in a very detailed manner. So here, For the f of t, the Fourier transform is f of omega. So f of omega is equal to integration of t is equal to minus f to plus t, f of t into e to the power of minus j omega t into dt. So I already told you the Laplace transform of f of s, which is f of s is equal to integration of t is equal to minus f to plus f of t into e to the power of minus xt into dt. In place of s to replace s by j omega, we are going to get the Fourier transform. So when you keep s is equal to j omega, the Laplace transform is going to become a Fourier transform. So therefore we are going to get is equal to integration of minus f to t is equal to minus f to plus f of t into e to the power of minus j omega t into dt. So here f of omega exists only if f of t is a finite energy signal. See, whenever f of t is always a finite energy signal, then only this integration is going to give you a finite value, then only it is going to exist. So we can say that always whenever the signal f of t is energy signal, then only this integration is a finite value, and then only this value is going to give some finite value, so it is going to exist. So f of omega exists only if f of t is a finite energy signal. See, I already told you here finite energy means integration of minus f to plus d mod of f of t into dt. See, the modulus of e to the power of minus j omega t is nothing but 1, because e to the power of j theta is equal to cos theta plus j sin theta, its magnitude is equal to 1. So therefore this magnitude is definitely equal to 1. So only these things that we are going to get. So therefore integration from minus f to plus into mod of f of t into dt is always less than infinity. Then only if this value is less than infinity, which is giving a finite value, then only f of omega is going to exist. So we can say that whenever the signal is said to be energy signal, this value is finite, so f of omega is going to exist. So then only Fourier transform of the f of t will exist. See, I can also specify like this, which is energy is nothing but energy of any signal is equal to integration from t is equal to minus f to plus into mod of f of t whole square into dt. If this is a finite value, then its k is also a finite value. So this is actually the energy. The energy of any signal means this is the actual expression of energy of any signal. If this is a finite value, then this is also finite value. So therefore, here simply we can say that here simply see it means that energy of signal should be finite, then only Fourier transform of f of t will exist. So this is what I am trying to tell you. See, whenever the energy of a signal, if it is a finite, definitely the Fourier transform is going to exist. The energy of a signal f of t is equal to e is equal to integration from t is equal to minus f to plus f t mod of f of t whole square into dt. So whenever the energy of a signal, if it is less than infinity or a finite value, then we are going to get the Fourier transform of that signal. As I already told you, which is mod of f of omega, the determinant of f of omega is always an even number, whereas phase angle of f of omega is always an odd function. So the determinant of f of omega is always an even function, whereas the phase angle of f of omega is always an odd function. Now the statement 3 basically time shifting theory. I have already told you the time shifting theory, which is for the f of t, the Fourier transform is f of omega, then f of t minus t means a time delay. A time delay is nothing but a time shift or time delay f of t minus t. But for this Fourier transform will be e to the power of minus j omega t into f of omega, because I have already told you f of t minus capital T, the Fourier transform is equal to e to the power of minus t s into f of s. In place of s substitute j omega, we are going to get this one, which is e to the power of minus j omega t into f of omega, because I have already told you for f of t minus capital T, the Laplace transform is equal to e to the power of minus s capital T into f of s. In place of s, if you substitute j omega, we are going to get the Fourier transform. So this is what that we are going to get. So we can show clearly there is a negative sign, but in the question they are not given this negative sign. So this is what that you always have to remember. Now the next one is called the statement 4, which is frequency shifting theorem. So frequency shifting theorem means we are going to shift the signal in the Fourier transform in the frequency domain. Then what is the change in the time domain we need to figure out. So for f of t, if the Fourier transform is f of omega, then for f of omega minus omega naught, a small shift in the frequency domain will give a signal which is f of t into e to the power of j omega naught t. So therefore, this is a very important one. We can easily find with the help of the formula also. So f of t into e to the power of j omega naught t will give you a Fourier transform of f of omega minus omega naught. So f of t into e to the power of j omega naught t will give you a Fourier transform of f of omega minus omega naught. So f of t into e to the power of j omega naught t will give me a Fourier transform of f of omega minus omega naught. So these are some of the important things that you always have to keep in your mind. So now we are going to solve another question. See the question here. Basically, the z transform and the ROC of the function f of n is equal to e to the power of n into u of n r. So we have to find what is the z transform and the ROC of the function f of n is equal to e to the power of n into u of n. We need to figure out the z transform and the ROC of the function f of n is equal to e to the power of n into u of n. So what is four options? Option A, 1 by 1 minus a into e to the power of minus 1 with a margin greater than mod a. So this is the z transform and also its ROC. So now we discuss this solution. So option is the correct solution of this question. So let's solve this numerical. So you can see clearly here in the question they are given we can say that the signal is equal to f of n is equal to e to the power of n into u of n. So we have to find what is the z transform and also its ROC. So f of z we need to figure out and ROC also and the ROC also we have to find. So what is the x of n? So let me assume this is x of n. So x of n is equal to e to the power of n into u of n. Its z transform x of z is equal to the formula sigma n is equal to minus n to plus n t x of n into d to the power of minus n. So this is the we can say that the z transform of any signal of x of n, which is x of z is equal to sigma n is equal to minus n to plus n to x of z x of n into d to the power of minus n. You can say clearly x of z is equal to sigma n is equal to minus n to plus n t and x of n is equal to which is e to the power of n into u of n into d to the power of minus n. As u of n is defined only from n is equal to 0 to infinity only. For minus n to minus 1 its value is equal to 0, so the value will become 0. So this summation is now it will converge from it will simplify to from sigma n is equal to 0 to plus infinity. Now the summation is from n is equal to 0 to infinity e to the power of n into because u of n is equal to 1 from n is equal to 0 to infinity. So we have to keep here 1 into 0 to the power of minus n. So now I am going to take n as a common. So therefore sigma n is equal to 0 to infinity a into 0 to the power of minus 1 whole to the power of n. Now if I keep these values n is equal to 0, n is equal to 1, n is equal to 2, then we are going to get, if you keep n is equal to 0, n to the power of 0 is nothing but 1 plus if you substitute n is equal to 1, we are going to get a to the power of minus 1 plus if you substitute n is equal to 2, we are going to get a to the power of minus 1 whole square. So basically this is called as the geometric series like AR square, AR cube up to infinity. So this summation will be converging only. The summation, see the geometric series will, the infinite geometric series will converge to only when mod of r is less than 1. So therefore the summation will be, it will converge to a by 1 minus r. So now x of z is nothing but here this all value will converge to, and value to the geometric series formula a plus ar square plus ar cube up to infinity. It will give a finite value to a by 1 minus r when mod of r is less than 1. So now here you can say clearly what is the mod of r. So a is equal to 1, and what is r is equal to a into the power of minus 1. So therefore here a is equal to 1 and r is equal to a into the power of minus 1. So a by 1 minus r. So a is equal to 1, r is equal to a into the power of minus 1. So if we substitute this formula, we are going to get 1 by 1 minus a into the power of minus 1. And what is the magnitude of r? The magnitude of the r should be always less than 1. So r is nothing but simply an r into a into the power of minus 1. This magnitude part should be always less than 1. So if you simplify this one, we are going to get 1 by 1 minus a into the power of minus 1. So if you simplify, we are going to get mod a by mod z less than 1 or mod a less than z, or you can say that here mod z is greater than mod a. So for the final, if you simplify this one, we are going to get x of z is equal to z by z minus a with mod a greater than a mod a. So mod z greater than mod a, or you can also get another function which is 1 by 1 minus a into the power of minus 1 with mod z greater than mod a. So this is the we can say that the z transform and its corresponding ROC. So only in this region the z transform is going to give you a finite value. Only in this region. So if I plot this graph, I am going to get with respect to the axis, we can say this is the z plane. So in the z plane, here if you take a circle of A radius, where mod z greater than mod A. So mod z greater than mod A means it is above this one, means outside this circle. So outside this circle only this ROC is going to get converged, but inside this one and on this one it is not going to get converged. So this is called as a ROC in terms of figure. So in terms of z plane, I am going to show in terms of figure like this graph. So we can say that for signal x of n is equal to the power of n into rho of n, if z transform is equal to z by z minus a with mod z greater than mod A, which is outside the circle of radius mod A. So this is called as the ROC. So now we are going to solve the other question. See the question here. A single phase half wave diode rectifier with input voltage 10 sin omega t is feeding into a resistive load of 100 ohm. The RMS value of the load current and the input power factor are respectively. So basically in this question they are given that a single phase half wave diode rectifier, diode rectifier with input voltage 10 sin omega t is feeding into a resistive load of 100 ohm. The RMS value of the load current and the input power factor. So basically they are given a single phase half wave diode rectifier and the input voltage they are given and also they are given a load resistance. So now based on this we have to find what is the RMS value of the load current and also input power factor we need to figure out. So these four options, option A 50 milliampere and 0.707 is the correct solution of this question. So let's solve this numerical. So you can say clearly a single phase half wave diode rectifier means this is a circuit. A single phase means the single phase supply. Half wave means in a 0 to 2 pi only half of the portion we are going to get a cycle and the remaining part we are not going to get any signal. So this is called as a half wave. So we are going to keep here diode here. So this is a circuit of a single phase half wave diode rectifier. And what is the input voltage? Input voltage is equal to Vs of t is equal to 10 sin omega t. So we are going to keep here diode and the load resistor R is equal to 100 ohm. So now we have to find what is that. Let me assume the source current is Is of t and this is the load current is I naught of t. As there is no any other extra branch, so we can say whatever source current is always equal to load current. But if any extra branch is there, definitely the source current will never be equal to load current. But here we have not kept any extra, there is no extra branch. So definitely Is of t is always equal to I naught of t. So now based on this we have to find what is the RMS value of the load current. So RMS value of load current is always equal to RMS value of supply current because there is no extra branch. And also input power factor we need to figure out. So I of t RMS value we have to find and also we have to find what is the input power factor we need to figure out. As we already told you, the source current is always equal to load current because there is no other extra branch. So because of this reason only we can say that always the source current is always equal to load current. So now here what we have to do basically here, this is the source voltage Vs of t, this is the input voltage Vs of t. So with the peak value of Vn and minus Vn. So for time period of t, half of the time period is a positive and remaining half period is a negative. So now I already told you the diode is going to connect only the positive cycle. So therefore if diode is on, so whatever the output voltage is equal to source voltage. So same here, same graph. What is source voltage? Same thing here we are going to get in the output voltage also. But in the remaining period, as the source voltage is negative, diode is going to get off. So therefore simply as diode is off, the output voltage is equal to 0. So this is the graph that we are going to get for the remaining cycle. So whenever diode is equal to on, V of t is equal to Vs of t. Whenever diode is equal to off, then V of t is equal to 0. Then similarly, if you want to draw the output current is equal to output voltage by resistor. So same graph we are going to get with a divided by resistor. So this is the peak value of voltage means the peak value of current is equal to Vn by R. As here output voltage is equal to 0, 0 by anything is Im 0. So here also same. The same graph but only peak values are going to get changed, which is for d is equal to 1, this is the graph. For d is equal to half, we are going to get this is the graph. So Im is equal to Vn by R. So now I want to find what is the RMS value of the output current. RMS value of output current, which is basically half wave rectifier, or we can say half wave rectifier signal, which is peak value by 2. For half wave signal, the RMS value is equal to peak value by 2. So peak value by 2, which is Im by 2. Im is equal to Vm by R. So Vm by R by 2 is nothing but Vm by 2 into R. So what is Vm? Vm is the peak value of the voltage, which is 10. So 10 by 2 into what is the value of R, which is 100. So if we solve this one, we are going to get 0.05 ampere, or simply we can say in terms of milliampere, which is 50 milliampere. So RMS value of the RMS value of the output current is equal to RMS value of the source current is equal to 50 ampere. So now the next thing we have to find is the input power factor we need to figure out. See, always as we are going to assume the diode is the ideal diode. So whatever the input power should be always equal to output power. Then what is the input power? Input power in terms of the RMS value, which is Vs RMS into Is RMS into cos phi. So Vs RMS into Is RMS into cos phi is equal to what is the output power? Output power is basically P the resistor. So output is basically P the resistor. So V RMS into I RMS, because its power factor is equal to 1 because both the signals are always in phase. So its power factor is equal to 1. So V RMS into I RMS. I already told you the output's current RMS value is equal to source current RMS value because both are same. So these two are going to get cancels. Then the cos phi is nothing but it's a ratio of the RMS value of the output voltage by RMS value of the source voltage. As I already told you, output is basically half wave signal. Its RMS value is equal to peak by 2. So peak value by 2, which is Vm by 2. Whereas Vs RMS is nothing but it is a full wave signal. So its RMS value is equal to Vm by root 2, peak value by root 2. So Vm by root 2. So if we solve this one, we are going to get 1 by 2 into root 2, which is equal to 1 by root 2. 1 by root 2 is nothing but 0.707. So what is the input power factor? Input power factor is always equal to 0.707. So always input power is equal to output power. So Vs RMS into Is RMS into cos phi is equal to V RMS into I RMS. So with this both are same. So input power factor is equal to RMS value of the input voltage by RMS value of the input voltage. So if you keep this one for half wave signal, out RMS value is equal to peak value by 2. Whereas for full wave signal it's RMS value is equal to peak value by root 2. So if you solve this one, finally we are going to get input power factor is equal to 0.707. So now we are going to solve the other question. See the question here. The number of converters required to design a 4-bit flash ADC is. So we have to find the number of converters which are required to design a 4-bit flash type ADC. We need to figure out. So the four options, option D, 15 is the correct solution of this question. So let's solve this numerical. So always the number of converters which are required to design a n-bit flash type ADC is always equal to the power of n minus 1. So to the power of n minus 1. So these are the number of converters which are required to design a n-bit flash type ADC. So these are the number of converters which are required to design a n-bit flash type ADC. So the number of converters which are required to design a n-bit flash type ADC is equal to the power of n minus 1. So for 4-bit flash type ADC we need to figure out. So for 4-bit means in place of n substitute n is equal to 4, then definitely we are going to get 2 to the power of 4 minus 1. 2 to the power of 4 is 16, 16 minus 1 is 15. So 15 number of converters are required to design a 4-bit flash type ADC. So finally I can say that the number of converters which are required to design a n-bit flash type ADC is equal to the power of n minus 1. So for 4-bit means substitute in place of n is equal to 4. So we are going to get 16 minus 1 is equal to 15. So finally I can say that the number of converters which are required to design a n-bit flash type ADC is equal to the power of n minus 1. So now the next question is, the highest frequency of a triangular wave of 20 volt peak to peak amplitude that can be reproduced by an op amp whose slew rate is 10 volt per microsecond will be. So basically in this question they are given a triangular waveform of 20 volt peak to peak amplitude. Then if you want to make this one as an output of the op amp, if the op amp is having a slew rate of 10 volt per microsecond, then what is the maximum frequency that can be applied, and the signal can be applied to op amp, we need to figure out, which is option C, 250 kilohertz is the correct solution of this question. So the highest frequency of a triangular wave of 20 volt peak to peak amplitude that can be reproduced by an op amp whose slew rate is 10 volt per microsecond will be option C, 250 kilohertz is the correct solution of this question. So let's solve this numerical. So we can say clearly here, let me assume a triangular waveform of this format. So triangular waveform of this format. So from here to here, which is half of the period t by 2, from here to here another half of, so another half of the period. So overall time period is t. So this is t by 2 and this is t by 2. So overall it is t. So t 20 volt peak to peak. So therefore this is plus 10 volt and this is minus 10 volt. So overall the peak to peak value is 20 volt. So output voltage peak to peak is equal to 20 volt. Then here always Now I want to find what is the slope of this triangular waveform I want to figure out. So what is the slope? Say I want to find the slope of this triangular waveform from here to here. The amount of change, the change is nothing but this height. This height is 20 volt and this with in terms of time it is t by 2. So the slope is nothing but which is the slope is equal to tan theta is equal to which is opposite by adjacent. Opposite is equal to 20 volt and this is t by 2. The slope of the triangular waveform is equal to 20 volt per t by 2 seconds. So therefore, the slope of the triangular waveform from figure is 20 volt per t by 2 seconds means the unit is volt per second. So this is the slope of the triangular waveform. But in the question they are given the slew rate of the op amp. The slew rate of the op amp is equal to 10 volt per microsecond. Then this force should be equal. So this force should be equal. Then only we can figure out the maximum frequency of the triangular waveform. We can figure out whenever these both are always equal. So slew rate is equal to 10 volt per microsecond. So microsecond is nothing but 10 to the power of minus 6 seconds. So if it goes upward, we are going to get 10 into 10 to the power of 6 volt per second. I already told you the slope should be always equal to slew rate. Then only we can find the maximum frequency. So slope should be always equal to slew rate. Slope is equal to 20 volt per, just 20 by t by 2, which is volt per second, and the slew rate is equal to 10 into 10 to the power of 6 volt per second and volt per second. So both should have the same unit, which is volt per second and volt per second. So now we have to do the equation. We have to equate these two things. The slope of the op amp is equal to, or we can say the slope of the triangular waveform is always equal to slew rate of the op amp. Then here we are going to get, which is 40 by t is equal to 10 into the power of 6. So t, if you solve this one, we are going to get 40 by 10 into the power of 6. So we got the value of t. So what is f? F is equal to 1 by t. So therefore, if we do the reverse of this one, we are going to get 10 into 10 to the power of 6 by 40. So if we solve this one, we are going to get finally, which is 250 into 10 to the power of 3 hertz, which is equal to 250 kilohertz. This unit is hertz. So if we solve this one, we are going to get 250 kilohertz. So 250 kilohertz is the maximum frequency of the triangular waveform that we can reproduce with the help of this op amp. So always to find the maximum frequency, always you have to equate the slew rate of the op amp is equal to slope of the triangular waveform. So now we are going to solve another question. See the question here. For the op amp circuit shown with the square wave input, the output waveform will be. So this is the op amp circuit they are given. So suppose if you are going to give an input as a square wave input, then what is the nature of the output we need to figure out. So these are the four options. So option B is the correct solution of this question. It is having a spikes. So we can see clearly there are spikes in the output voltage. We can see clearly. So option B is the correct solution of this question. So this is basically negative feedback circuit. So it is a negative feedback circuit, and also it is a input is given to the inverting terminal. So it is called as the inverting amplifier, or we can say inverting op amp. But there is a capacitor and also resistor. So now we'll see something more about this one. So we have, suppose if you are going to give a square wave input for this op amp, then we need to find what is the output voltage we need to figure out. So option B is the correct solution of this question. So let's solve this numerical. So as you can see clearly, this is the figure that is given in the question. So this is a plus or minus V naught of t capacitor. This is a feedback resistor, and this is something Rx is equal to Rf they are given. So now we have to find what is the output voltage we need to figure out. As I already told you, it is a negative feedback amplifier. So input impedance is very higher. So input impedance is very higher. So input current is always equal to 0 here. So here also input current is equal to 0. But as input current is equal to 0, then what of this voltage drop is equal to same voltage. So 0 volt. So with the help of virtual short, this is also same voltage. So therefore, see, the electrolysis of the current is I here. So in this branch the current is I. As current here it is 0. So with the help of KCL, what is the incoming current should be always equal to outgoing current. So here also current is I. So now I am going to apply the KCL, or we can say I am going to apply the Ohm's law to get the equation between the input and the output. Then what is the value of I? I is equal to the current in the capacitor is nothing but I is equal to C dt. The voltage difference is V naught of t and 0. So therefore, I is equal to C1 into D, V of t minus 0 by dt is equal to same current here also 0 minus V naught by Rf. 0 minus V naught by Rf. So if we equate these two equations, we are going to get C1 into dVi by dt is equal to minus V naught by Rf. So V naught is equal to minus Rf into C1 into dVi by dt. As you can see clearly, output voltage is the differentiation of the input voltage. So we can say it is a differentiated circuit because the output voltage is the differentiation of the So output voltage is the differentiation of the input voltage. So it is said to be a differentiator circuit. So V0 is equal to minus Rf into C1 into dVi by dt. As you can see clearly, the output voltage is the differentiation of the input voltage. So it is said to be a differentiator circuit. So as you can see clearly, V0 is equal to minus Rf into C1 into dVi by dt. As the output voltage is the differentiation of the input voltage, so it is said to be a differentiator circuit. So see, whenever we give a square wave input for differentiator, definitely here the differentiation, it's a constant signal, so differentiation is equal to 0. Here also constant, again differentiation is equal to 0, but there is a sudden change of voltage in this small amount of time, so there will be spikes in this small amount of duration. So therefore, whenever you give a square wave input to a differentiator, the output voltage will be a spike signal. So therefore, the given circuit is a differentiator. If you give a square wave input is applied to a differentiator circuit, then the output voltage will have spikes. I have already told you it is a differentiator circuit. So if you give a square wave signal, the output waveform will be always a spikes. So this is the input voltage that I have given. So you can see clearly it is a square wave input. So here it is 0, here it is 0, here it is 0, here it is 0. Here it is 0 in the output waveform. But here a sudden rise in voltage. A sudden rise in voltage means that differentiation is positive, but there is a negative here. So negative spikes we are going to get. But here there is a decrease in voltage. Sudden decrease in voltage means differentiation is negative. So again there is a negative. So negative to negative is again positive. So we are going to get a positive spike here. Again there is a sudden rise in voltage. Rise in voltage means the differentiation is positive. So positive to negative is again negative. So we are going to get a negative spike here. Similarly here also there is a sudden decrease in voltage. So decrease in voltage means slope is equal to negative. So negative to negative is positive. So we are going to get a positive spike. So this is the spikes that we are going to get. So this is the nature of the spikes that we are going to get. So this is the output voltage waveform. So whenever you give a square wave input to a differentiator circuit, the output waveform will be always a spikes waveform. So now we are going to discuss the other question. See the question here. In rotor angle of stability, what is the condition for stability? So in the rotor angle of stability, we have to find what is the basic condition for stability. So there is 4 options. Option B, d delta by dt is equal to 0. So d delta by dt is equal to 0 is the basic condition for, it's the basic condition for stability in the rotor angle of stability. So in the rotor angle of stability, the condition for stability is basically d delta by dt is equal to 0. So now we'll discuss something more about this one. See, always for rotor angular stability, d delta by dt is equal to 0, then only we can say that system is said to be stable. So in the rotor angular stability, always d delta by dt is always equal to 0, then only we can say that system is said to be stable. So this is the basic condition for stability in the rotor angular. So therefore, for rotor angular stability, always d delta by dt is equal to 0, then only the system is said to be stable. For rotor angular stability, the condition for stability is basically d delta by dt is equal to 0. So in the rotor angular stability, the condition for stability is always d delta by dt is equal to 0. Rotor angular stability is the ability of interconnected synchronous motion of a power system to remain in synchronism even after being subject to a disturbance. So basically what is the meaning of rotor angular stability means? It is the ability of the interconnected synchronous machines of a power system to remain in synchronism even after being subject to a disturbance. As I already told you, in the power system, all the generators are being connected in parallel. Even there is a disturbance in the overall power system, even then these synchronous machines are still in synchronism because of this condition only. So the rotor angular stability is the ability of the interconnected synchronous machines of the power system to remain in synchronism even after being subjected to a disturbance. So even after subject to a disturbance, still they are in the synchronism, then it is called the rotor angular stability. So rotor angular stability is the ability of the interconnected synchronous machines of a power system to remain in synchronism even after being subjected to a disturbance. So now I will discuss there are two types of disturbances are there, which is small disturbance and also large disturbance. Small disturbance is also called as the small signal stability, and the large disturbance is also called as the transient stability. So we are going to see there are two types of disturbances which are going to occur in the power system network, which are small disturbance or the large disturbance. Small disturbance is also called as the small signal stability, and the large disturbance is also called as the transient stability. So now we'll see each and every aspect regarding the small disturbance and also the large disturbance. Ability to maintain synchronism under small disturbance. For a small disturbance, when the system is being under synchronism, it is called as a small disturbance. Ability to remain in synchronism even after small disturbances. Here it is ability to maintain in synchronism even after large disturbances. So this is a basic point here. Since disturbances are small, non-linear differential equations can be linearized. So in this small simple analysis, we can say as the disturbances are very small in magnitude, so the non-linear differential equations can be linearized. But this is not the case in this one, which is since disturbances are large, non-linear differential equations cannot be linearized. So in this one, as the disturbances are very large, so we cannot do the non-linearized into linearized. So we cannot linearize this non-linear differential equations. So as I already told you, these are always linear equations, so it is very easy to solve. So these are very easy to solve, but here it has to be solved numerically, and it is very difficult because these are non-linear equations. You have to solve it numerically, and it is a very severe pain in the neck, or simply we can say it is very difficult. However, we can use a graphical approach called the equal area criteria for analyzing the stability of a single machine connected to an infrared bus using the classical method. I already told you that equal area criteria is used for analyzing the transient stability. So whenever the accelerating area is equal to decelerating area, then the system is said to be stable, otherwise it is unstable system. That is for the transient stability, or is also called as the large disturbances stability. So these are very non-linear equations, non-linear differential equations. So therefore, it is a very hard to solve and it is a very difficult. So however, we can use a classical method, which is called as the graphical approach, which is equal area criteria. So for analyzing the stability of a single machine connected to an infrared bus using the classical method, which is called as the equal area criteria. So finally, I can say that for rotor angular stability, d delta by dt is equal to 0, then only the system is simply stable. For rotor angular stability, the condition for stability is only d delta by dt is equal to 0, and the rotor angular stability is the ability of the interconnected synchronous machines of a power system to remain in synchronism even after being subject to disturbance. I already told you disturbance of two types. One is called the small disturbance or small signal stability. The second one is the large disturbance of the transient stability. So now we differentiate each and everything. In the small signal, it is the ability to maintain synchronism even under small disturbances. Whereas in the large disturbance, it is the ability to maintain synchronism even after large disturbance. In the small signal, I have already told you here, these disturbances are very small, or we can say small in magnitude, so non-linear differential equations can be linearized and it is very easy to solve. Whereas here, since disturbances are very large, so large in magnitude, so non-linear differential equations cannot be linearized, so it is very severe hard to solve because this can be solved by numerical method, so it is very difficult. So then we have to use the classical method, which is called the graphical method or the equal area criteria method for analyzing this transient stability. Because I already told you equal area criteria is only for analyzing the transient stability because there the disturbance is very large. So whenever the accelerating area is equal to decelerating area, then the system is stable, otherwise it is unstable system. So however, we can use the graphical approach called the equal area criteria for analyzing the stability of a single machine connected to an infinite bus using the classical method. So now we are going to solve another question. See the question here. A transmission line is operating with a phase shift of 8 degrees between the two ends. If the load is suddenly increased, then what is the nature of the phase displacement we have to find? It will increase. The phase displacement will increase. Since See, whenever the load demand increases, means the power demand increases. So whenever the power demand increases, then the angle also increases. So therefore, the phase displacement will increase. So option is the correct solution of this question. So therefore, a transmission line is operating with a phase shift of 8 degrees between two ends. If the load is suddenly increased, then the phase displacement will increase. So now we'll discuss the exact solution of this one. So as you can see clearly here, there is a power transmission line, the generator here. This is the bus 1 and this is the bus 2, sending in bus and receiving in bus. So there is a load we are going to connect here. So this generator is going to send a power of P1 and this load is going to deliver a power of, it is going to receive a power of P2. As it is a purely resistive, it's a purely inductive I am going to assume. So whatever the input active power should be always equal to the receiving active power, because it will never consume the active power, it will only consume the reactive power. So therefore P1 is always equal to P2, and this bus voltage is something that this bus voltage is equal to mod of V1 at an angle of delta 1, and this voltage is nothing but mod of V2 at an angle of delta 2. So this is the bus 1 and this is the bus 2. So bus 1 voltage is V1 bar is equal to mod of V1 at an angle of delta 1, and bus 2 V2 bar is equal to mod of V2 at an angle of V2. So bus 1 voltage is V1 bar, bus 2 voltage is equal to V2 bar, which is landed on the and angle also here delta 1 and delta 2. So what is the active power flowing through this line is equal to P1 is equal to P2 is equal to mod of V1 to mod of V2 by, which is this line transformer inductive part, the reactance part, which is XL into sine of delta 1 minus delta 2. So this is the phase difference between the phase displacement between this delta 1 and delta 2, which is delta 1 minus delta 2. So this delta 1 minus delta 2 I am going to assume which is delta. This delta is called as the phase difference or the phase displacement between the vectors V1 bar and V2 bar. So this is the bus voltages, bus 1 voltage and bus 2 voltages. For these two vectors, the angle between these two vectors is called as the delta. So delta is called as the phase displacement between the two voltage vectors V1 bar and V2 bar. So delta is called as the phase displacement between the two voltage vectors V1 bar and V2 bar, which is delta is equal to delta 1 minus delta 2 is the phase difference between the two voltage vectors of V1 bar and V2 bar. But these delta 1 and delta 2 with respect to a 0, with respect to positive x-axis, with respect to a reference, but this delta is the phase displacement or phase angle between these two vectors, but this delta 1 and delta 2 with respect to some reference axis, whereas this delta is the phase displacement between these two vectors, between these two voltage vectors, which is V1 bar and V2 bar. So this is a very important point that you always have to understand. So now I can replace this delta 1 minus delta 2 is nothing but delta, and now I am going to draw the diagram of this equation. So if I draw the power angle diagram, we are going to get, which is P is equal to mod of V1 mod of V2 by XL into sine of delta, which is this is the delta. Then we are going to get like this, like a sine graph we are going to get. So this is the P1 is equal to P2. So this is the, at 90 degree we are going to get a maximum power. But in the question they are given that initially it is operating at the 80 degree. Suddenly the load is increased. So whenever the load increases, the power demand increases. So this has to submit more amount of power. So it has to, this generator has to give more amount of power. So this curve is going to move. As the curve moves upward, this delta also will increase. So therefore, the phase displacement between the two voltage vectors V1 bar and V2 bar also increases. So whenever the load demand increases, the power demand increases. So net power increases. So therefore delta is the phase difference between the phase displacement between the two voltage vectors V1 bar and V2 bar. It is also increases. You can see clearly from this graph also. So finally I can say that as a load demand increases, power P1 is equal to P2, they are also going to get increased, because as load demand increases, power the sending by the generator is also increases. So as power increases, the delta is also increases. So therefore finally we can say the phase displacement between the two voltage vectors will increase. So therefore as load is increased, then the phase displacement also increases. So this is the conclusion of this concept. So now we are going to solve another question. See the question here. If the regulation R is equal to 1% and the damping coefficient D is equal to 0.8, the change in the generation of the area for a drop in frequency of 0.0015 per unit is. So basically the question they are given a regulation R is equal to 1%, means in terms of per unit is equal to 0.01 per unit, and damping coefficient D is equal to 0.8. The change in generation of the area for a drop in frequency of 0.0015 per unit in P we need to figure out. So what is 4 options? Option C, 0.15 is the correct solution of this question. So here, basically, in a given area, the frequency is dropped by a per unit of 0.0015, and also the regulation is equal to R percentage. So based on this, we have to find what is the power generation we need to figure out. The change in generation of the area we need to figure out. So what is 4 options? Option C is the correct solution of this question. So let's solve this numerical. The question, they have given regulation. So they have given basically the regulation. The regulation is equal to R is equal to 1%, means in terms of per unit, which is 0.01 per unit. So R is nothing but regulation, which is 1%, means in terms of per unit, which is 0.01 per unit. And also they have given the damping coefficient. This called as the damping coefficient, its value is equal to 0.8. And also they have given that in a given area, there is a drop of frequency. Drop of frequency means change in frequency, delta F is equal to drop in frequency. They are given the frequency is a drop. Drop means basically negative. We have to use here negative. Rise in frequency means plus. You have to use positive. Drop in frequency means the frequency is decrease. So you have to use the negative sign. So it is a sign sensitive. Always the delta F is always a sign sensitive. So you have to always use the sign sensitive. So therefore, whenever the frequency drop means you have to use negative. Whenever the frequency is rise means you have to use positive. So in the question they are given the change in frequency is a drop. So drop in frequency means you have to use negative. So minus 0.0015 per unit. So now we have to find what is the power generation. So change in power generation, which is contributed by load, we need to figure out. So therefore, we can say how much amount of change in generation in that area we need to figure out. Or simply the change in generation which is contributed by load we need to figure out. The basic formula is equal to delta Pg is equal to minus delta F by R. It's a very important formula. So if you know this formula, you can easily solve this question. As you can see clearly, this formula is independent of the damping coefficient. There is nothing like damping factor. So therefore, we can say delta Pg is equal to minus delta F by R. So delta F is always a sign sensitive equation, sign sensitive term. So delta Pg is equal to minus delta F by R. So delta Pg is equal to minus delta F by R. So we know the value of delta F, we know the value of R. So substitute here, and if you simplify, we are going to get the value of delta Pg. So now I have substituted the value of the, which is delta F, which is minus 0.0015, and also I have substituted the value of the R. Then I have solved this one, we are going to get which is plus 0.15 per unit. So delta Pg is nothing but, which is a positive value, which is 0.15 per unit. So this is the point that you always have to understand, which is delta Pg is equal to minus delta F by R. The delta F is a change in frequency, it is always a sign sensitive. So you have to use positive for rise in frequency, negative for drop in frequency. So there is a very important form that you always have to remember. So delta F is equal to negative whenever the frequency is a drop in frequency, and it is a positive whenever the rise in frequency, and delta F is always a sign sensitive. So now we are going to solve the another question. See the question here. In WLG fault, the relation between the sequence voltages is. So these 4 options, option A or B, both are correct. So both are correct based on the condition. Suppose if the fault impedance is equal to 0, then this is the we are going to get. If fault impedance is not equal to 0 means this is the condition that we are going to get. So if fault impedance is equal to 0, then we are going to get the option B. If the fault impedance is not equal to 0, then we are going to get the option A. So both are correct statements, A or B. So in the WLG fault, both are correct. So now we'll discuss the exact solution of this question. So you can see clearly here, basically I will discuss about the 3 important faults which are called as the LG fault, WL fault and the WLG fault. So the initial one is the LG fault. In the LG fault, we can see clearly here the positive sequence component and negative sequence component and the zero sequence component. Is Z1, Vg, Z2, and Z0 and 3Zn. So these three sequence components are going to come in series fashion. So this is IR1, IR2 and IR0. So you can see clearly these are counted in the series fashion like this. With this impedance is equal to 3 times of ZF. The ZF is called as the fault impedance. So you can see clearly that the IR1 is equal to IR2 is equal to IR3 because it is a series circuit. So therefore, the positive sequence current is equal to negative sequence current is equal to zero sequence current in case of the LG fault. And this is the VR1, this is VR2 and this is VR0. So this is in case of LG fault. In case of LG fault, the positive sequence current is equal to negative sequence current is equal to zero sequence current. And this is the these three sequence networks are going to connect in a series fashion. So IR1 is equal to IR2 is equal to IR0. Suppose if you go for the double fault, in case of double fault, you can see only positive sequence and negative sequence are going to connect in a parallel fashion, but we are going to open circuit the zero sequence component. So therefore, we are going to get Z1, Vg, IR1, Z2, IR2, plus or minus VR1, plus or minus VR2. They are going to connect in a parallel with a fault impedance. In between them, there is a fault impedance. So you can see clearly IR1 is equal to minus IR2 and IR0 is equal to 0 and VR0 is equal to 0. So, but if ZF is equal to 0, then VR1 is equal to VR2. If suppose ZF is not equal to 0, then VR1 is not equal to VR2. So these are the conditions that you are going to get. So listen carefully. Whenever ZF is equal to 0, then VR1 is equal to VR2. If ZF is not equal to 0, then VR1 is not equal to VR2. So this is the conditions that you are going to get in terms of the LG in the LL fault. In the LL fault, these are the conditions that we are going to get, which is IR1 is equal to minus IR2 and IR0 is always equal to 0 and VR0 is always equal to 0. If ZF is equal to 0, if ZF is equal to 0, then VR1 is equal to VR2. If ZF is not equal to 0, then VR1 is not equal to VR2. So same thing we have written. When ZF is equal to 0, then VR1 is equal to VR2. If ZF is not equal to 0, then VR1 is not equal to VR2. So these are the conditions that we are going to get in terms of double fault. So one important point that we always have to remember, see, if a fault is having a ground fault, then definitely zero sequence component is not equal to 0. So you can see clearly this fault is a ground fault, so zero sequence component is not equal to 0. But here this is not a ground fault, so therefore the zero sequence component is equal to 0. So whenever a fault is having a ground, definitely the zero sequence component is non-zero. If a fault is not having any ground fault, then definitely the zero sequence component is equal to 0. So finally I can say that whenever a fault is a ground fault, then its zero sequence component is always not equal to 0. So now I will discuss the WLG fault. So based on this only the question they asked. So now I will discuss what is the WLG fault. In a WLG fault, all the sequence networks are going to cut in a parallel with a impedance of 3ZF here. So with the impedance of 3ZF here. So this is the positive sequence network, negative sequence network and the zero sequence network. Z1, Vg plus or minus VR1, IR1. Z2, IR2 plus or minus VR2. Z0, Zn, IR0 plus or minus VR0. So you can see clearly if you apply the KCL at this junction, IR1 plus IR2 plus IR0 is equal to 0. If ZF is equal to 0, then VR1 is equal to VR2 is equal to VR0. If ZF is not equal to 0, then VR1 is equal to VR2 only. So I already told you IR1 plus IR2 plus IR0 is equal to 0. When ZF is equal to 0, then VR1 is equal to VR2 is equal to VR0. If ZF is not equal to 0 means VR1 is equal to VR2. So when ZF is not equal to 0, then VR1 is equal to VR2. So these things I already told you. In the question they are given this one and also this one. So based on the conditions we are going to get the two things. So option A and option B both are correct solutions of this question. So finally I can say that when it is a ground fault, then zero sequence current is non-zero, otherwise it is 0. I already told you, if a fault is having a ground fault, then its a zero sequence component is always not equal to 0, otherwise it is always equal to 0. This concept also I have already told you. So therefore, if a fault is having a ground fault, then always its zero sequence component is always not equal to 0, otherwise it is always equal to 0. So this is a concept that you always have to remember. So when it is a ground fault, then zero sequence current is always non-zero, otherwise it is 0. So finally I can say that in the double fault, in the LG fault, initial fault is the LG fault, in the LG fault all the sequence numbers are cut in a series fashion, whereas in the double fault only the positive sequence and negative sequence we are going to count in parallel. The last one is called the WLG fault. In the WLG fault, all the sequence numbers are going to count in a parallel. So this is the thing that you always have to keep in your mind. So now we are going to solve another question. See the question here. A large power system is represented by a Thevenin's equivalent. The ETH and the ZTH are 0.9 at an angle of 0 per unit and 0.25 at an angle of 90 degree per unit respectively. If a shunt capacitor bank is connected to raise the bus voltage to 1 per unit, the MVAR rating of the capacitor bank is assume base MVA of 100 and base kV of 138. So basically they are given, actually this is base KV, not KVA. This is base KV and this is a base MVA. This is for reading of MVA and this is for KV. This is not KVA, it is KV. So 138. So now based on this we have to find what is the rating, the MVA rating of the capacitor we need to figure out. So basically here a large power system we are going to represent with the help of a Thevenin network like Thevenin voltage and Thevenin impedance across the bus. So this capacitor we are going to keep across the bus to raise the bus bar voltage to 1 per unit. Then we have to find what is the MVA rating of the capacitor we need to figure out. We are going to keep all these per units based on this rating which are called as a base MVA of 100 and base KV of 138. So these 4 options, option D, 40 is the correct solution of this question. So let's solve this numerical. See, this is the bus. So across this bus, I have already told you, across this bus I am going to represent the overall power system with a Thevenin voltage and Thevenin impedance. So across this bus, overall power system, overall complex power system, we are going to represent by simple Thevenin voltage and Thevenin impedance. Thevenin voltage is equal to 0.9 at an angle of 0 per unit is nothing but simple 0.9 per unit, and the Thevenin impedance is equal to 0.25 at an angle of 90 degree per unit is nothing but angle 90. It is a polar in terms of rectangle which is 0.25 J per unit. So now across this bus we are going to keep a capacitor of reactance XC. XC is the reactance of this capacitor we are going to keep. So therefore it is going to keep the bus bar voltage. Bus bar voltage is equal to 1 per unit. Means this voltage with respect to this one and this one, with respect to this node voltage and ground, its voltage is equal to 1 per unit. So now we have to find what is the reading of this capacitor we need to figure out. See, capacitor is going to, let me assume this capacitor is going to deliver a current of I, current in this direction. See, as we are not going to keep any load here, so whatever the same current is also going to pass through in this line also. So whatever the same current is also going to pass in this line also, because I am going to assume I have not kept any load here. So same current is also passing through this one. So therefore now this voltage we know, this voltage we know. So what is the value of current I? I is equal to this voltage minus this voltage by Z. Higher voltage minus lower voltage by impedance. V minus ETH by ZTH. V is nothing but 1. ETH is equal to 0.9 by ZTH is equal to 0.25 at an angle of J. So if we solve this one, we are going to get 0.1 by 0.25 J. But I want only the magnitude part of the current. I want only the magnitude part of the current, which is 0.1 by 0.25. If you solve this one, we are going to get finally 0.4 in terms of per unit, because all the voltages and the impedance are in terms of per unit. So its current is also, the magnitude part is also per unit, which is 0.4 per unit. So now I know the voltage, I know the current. See, I know the voltage across the capacitor, I know the current in the capacitor. Then what is the reactive power? Reactive power is equal to voltage into current, voltage into current. What is the reactive power? Reactive power is equal to voltage into current. So voltage into current. What is the voltage across the capacitor, which is 1 per unit? And what is the current of the capacitor, which is 0.4 per unit? So 1 into 0.4 is nothing but 0.4 per unit. So this is basically in terms of per unit. But what is the base MVA? Base MVA is nothing but SB is equal to 100 MVA. Then what is the per unit? Per unit is always equal to actual value by base value. So Q per unit is equal to Q actual by S base. Then what is Q actual? Q actual is equal to Q per unit into S base. Q per unit is nothing but 0.4 into S base is 100 MVA. So 0.4 into 100 is nothing but 40 MVAR. This is MVA. So it will become now MVAR. So therefore, the actual value, the actual rating of the capacitor is equal to 40 MVAR. So this is the correct solution of this question. There's another question. See the question here. Compared to the Newton-Raphson polar load flow, the fast breakable load flow will take more number of iterations. So basically, always the Newton-Raphson method will have less number of iterations when compared to any other method. So this is a very important thing to always have to keep in your mind. The Newton-Raphson method will always take less number of iterations when compared to any other method. So we can say that basically, compared to the Newton-Raphson polar load flow, the fast breakable load flow will take more number of iterations. Or simply we can say Newton-Raphson method will always take less number of iterations to get a solution when compared to any other method. So option B is the correct solution of this question. So therefore, the fast breakable load flow will take more number of iterations when compared to the Newton-Raphson method. So now I am going to compare the Newton-Raphson method and also fast decoupled load flow. So listen carefully. I am going to compare some of the important points regarding the Newton-Raphson method and also the fast decoupled load flow methods. In the Newton-Raphson method, we are going to get it requires less number of iterations to reach a convergence. So it is going to basically requires less number of iterations to reach the convergence, and the accuracy is also very high in case of Newton-Raphson method. So it requires less number of iterations to reach a convergence, and also its accuracy is very high. If number of buses are increased, then the complexity increases. So if you increase the number of buses, then the complexity of the analysis also increases. So if you increase the number of buses, then the complexity of the analysis also will increase. And the solution technique is very difficult. And the Jacobian matrix is also very complex in case of Newton-Raphson method. So simply we can say that in the Newton-Raphson method, it is going to requires less number of iterations to reach the convergence, and the accuracy is also very high. But if the number of buses increases, then the complexity of the analysis will increase. So now the solution technique will become very hard, and the Jacobian matrix is also very complex. Whereas in case of the fast decoupled load flow, it requires more number of iterations than the Newton-Raphson method to reach the convergence. So fast decoupled load flow will require more number of iterations to reach the convergence than the Newton-Raphson method. And also I already told you, accuracy is very less because of the approximations taken, because we are going to take a lot of approximations in this one, so accuracy is also very less. So due to the approximations, not that much complexity accuracy. As we are taking the approximate, accuracy is less, but the complexity will decrease. And the solution technique is very simple compared to the others. And Jacobian matrix is also very simple. So this is the important comparison between the Newton-Raphson method and the fast decoupled method. So I can say that in the Newton-Raphson method, it requires the less number of iterations to reach the convergence, whereas the accuracy is very high, and if the number of buses increases, then the complexity will increase, and the solution technique is very difficult, and Jacobian matrix is also very complex. Whereas in the case of the fast decoupled load flow method, it requires less number of iterations than a Newton-Raphson method to reach the convergence, and the accuracy is less because of the approximations taken. So due to approximations, not that much complexity occurs, and the solution technique is very simple compared to the others, and Jacobian matrix is very simple. So this is the major difference between the Newton-Raphson method and also the fast decoupled load flow method. So let me give you some more important analysis between the Newton-Raphson method and the Gauss-Seidel method. So now I am going to further do the analysis of the Newton-Raphson method and also the Gauss-Seidel method. So in this, the load flow equations are nonlinear in polar coordinates. So what are the load equations? The load flow equations are nonlinear in the polar coordinates, and it has quadratic convergence characteristics, more memory requirement, and the computation time per iteration is very more, and it requires a small number of iterations to reach the convergence. See, it requires less number of iterations to reach the convergence, but for each iteration it requires more number of time. So total time taken to get convergence is very less, and the number of iterations is independent of the size of the system. So whatever the number of iterations is independent of the size of the system, and the convergent criteria is independent of the selection of the slack bus. So convergent criteria is independent of the selection of the slack bus, and it is very reliable, very convergent, more accurate. It can be used for larger power system also. So these are some of the important characteristics of the Newton-Raphson method. So we can say the load flow equations are nonlinear in the polar coordinates. It has a quadratic convergence characteristics and the more memory requirement, and the computation time per iteration is very more, and it requires a small number of iterations to reach the convergence. So total time taken to get the convergence is very less, and the number of iterations is independent of the size of the system. The convergent criteria is independent of the selection of the slack bus, and it is reliable, convergent, more accurate. It can be used for larger power system also. Now we will discuss some important points regarding the Gauss-Seidel method. See, load flow equations are nonlinear in rectangular coordinates. It has linear convergence characteristics and less memory requirement, and the computation time per iteration is less, but it requires large number of iterations to reach the convergence. So total time taken to get the convergence is very higher, and the number of iterations required to get for convergence increases with the size of the system, that is number of buses. as the selection of the slack buses changes, the convergence criteria also will changes. It is very unreliable and it is convergent, less accurate, and will used for smaller system. So used for smaller power system only. So these are some of the important points regarding the Newton-Raphson method and the Gauss-Seidel method. So basically, Newton-Raphson method means it is the load flow equations are non-linear in polar coordinates, and it has the quadratic convergence characteristics, and it requires more amount of memory, and the completion time per iteration is more. So therefore, it requires a small number of iterations to reach the convergence. But the total time taken to get convergence is less. The number of iterations is independent of the size of the system. The convergent criteria is independent of the selection of the slack bus. It is very reliable, very convergent, more accurate. It can be used for larger power system also. Whereas the Gauss-Seidel method, in this the load flow equations are nonlinear in the rectangular coordinates. It has linear convergent characteristics, and the computation time per iteration is very less, and it requires large number of iterations to reach the convergence. Total time taken to get the convergence is very higher. The number of iterations required to get for convergence increases with the size of the system to this number of buses. So as the selection of this slack buses changes, the convergence criteria also will change. It is very unreliable and is unconvergent, less accurate, and it is used for the smaller power plant only. So finally I can say that this is the basic difference between the Newton-Raphson method and the Gauss-Seidel method. So finally I can say that compared to Gauss-Seidel method, Newton-Raphson method takes less number of iterations and more time per iteration. And what I told you in the Newton-Raphson method, see, the number of iterations are very less, but for each iteration the amount of time taken is very more. So therefore, compared to Gauss-Seidel method, Newton-Raphson method takes less number of iterations, but for each iteration the amount of time taken is very higher. So this is a very important point here. Basically, there are four parameters in the power system chart. There are basically four parameters in the power system chart: the P, Q, mod of E, and delta, are to be properly selected for optimum design of the power system network. So the four parameters are the P, Q, mod of E, and delta are to be properly selected for the optimum design of the power system network. There are three load flow methods are used in the load flow studies. There are basically three load flow methods which are used for the analysis of the load flow studies. They are basically Gauss-Seidel method, Newton-Raphson method, and the fast decoupled method. And already told you there are basically four parameters which are the P, Q, mod of E, and delta, which are to be selected properly for the optimum design of the power system network. And there are basically three load flow methods. There are basically three load flow methods which are used for the analysis of the load flow studies. They are the Gauss-Seidel method, Newton-Raphson method, and the fast decoupled method. So finally, I am going to give the conclusion of all the three methods. So you see clearly Gauss-Seidel method, Newton-Raphson method, and the fast decoupled load flow method. See, Gauss-Seidel method, it requires large number of iterations to reach the convergence, whereas this requires less number of iterations to reach the convergence. It also requires more number of iterations than Newton-Raphson method. So finally, out of these three methods, Newton-Raphson method always requires less number of iterations when compared to remaining two methods. So always, the Newton-Raphson method will always require less number of iterations when compared to remaining two methods. Whereas here, computation time per iteration is very less. Here computation time per iteration is more. Here computation time per iteration is less. It is very less when compared to this method. So out of these three methods, the computation time per iteration is very more for NR. It is very less for fast decoupled load flow. So therefore, the computation time per each iteration is very more in the Newton-Raphson method, and it is very less in the fast decoupled load flow method. It has linear convergence characteristics, which is this is called the Gauss-Seidel method as the linear convergence characteristics, whereas Newton-Raphson method has the quadratic convergence characteristics. The number of iterations required for convergence increases with the size of the bus. I already told you, as the size of the bus increases for the Gauss-Seidel method, the number of iterations will increase. But here, the number of iterations are independent of the size of the system. And already told you, independent of the size of the system, the number of iterations are always same. Whereas here, the number of iterations are independent of the size of the system. So these both are independent of the size of the system. These both are independent of the size of the system. But here, this is going dependent upon the size of the system. As the size of the system increases, the number of iterations will increase. So this requires less memory requirement, whereas here it requires more memory requirement. Here less memory requirement than Newton-Raphson method. So out of these three, more requirement, more memory requirement for the NR method and very less memory requirement for the NR for the fast decoupled mode form method. See, finally I can give conclusion regarding all these three methods. See, only Newton-Raphson method will require the less number of iterations when compared to the remaining two methods. And the completion time per iteration is very more for the NR method and it is very less for the fast decoupled mode form method. The number of iterations are depending on the size of the system. As the size of the system increases, the iterations increases for the Gaussian method, whereas it is independent. The number of iterations are independent for independent size of system. The number of iterations are independent size of system for the Newton-Raphson method and also for the fast decoupled mode flow method. And Newton-Raphson method requires more memory requirement and less memory requirement is for the fast decoupled mode flow method. So these are the important characteristics, final characteristics of the three methods: Gaussian method, Newton-Raphson method, and also the fast decoupled mode flow methods. So now we are going to solve the another question. See the question here. An induction motor is started with a star delta starter. The starting current and starting torque compared to direct online starting are reduced by. So in this question basically they are asking about the induction motor. We are going to use the star delta starter. Means initially we are going for the star and then later after some time we are going to go for the delta connection of the stator winding. So stator winding initially we are going to connect in a star connection and then we are going to connect in a delta fashion. Then if you are going to compare the starting current and the starting torque, because of star connection and the delta connection, what is the factor they are going to get reduced. So therefore the starting current in star connection is always equal to 1 by 3 times the starting current of delta connection or DOL. Similarly, the starting torque in a star connection is always equal to 1 by 3 times the starting torque of a delta connection. So this is the thing that you are going to get, which is 1 by 3 and 1 by 3. So both are going to reduce by a factor of 1 by 3. So basically dual is also called as direct. We are going to connect in a delta fashion. So star delta means initially we are going to go for the star and then we are going to go for the delta. So we basically starting current, or we can say the starting torque is always directly proportional to phase voltage whole square, and the starting current means basically we are going to compare the line currents. So now we'll discuss the exact solution of this question. So initially I am going to connect the stator winding in a star connection. So each star connection means each phase will have certain impedance. Let me also reduce the impedance of the one phase winding. Then what is the phase current in a star connection? Always phase current is equal to line current. So what is the phase current? Phase current is equal to phase voltage by impedance of the phase. So phase voltage is equal to, in a star connection, line voltage by root 3, V by root 3 by Z. So we are going to get V by root 3 into Z. I already told you in a star connection, phase current is equal to line current is equal to same value, which is V by root 3 Z. And this is the equation that we are going to get. Let me assume this is the equation 1. Then starting torque is always directly proportional to phase voltage whole square. If you remove this proportionality constant, let me assume it's a K. So I already told you K is K into V whole square. In a star connection, what is the phase voltage is equal to line voltage by root 3. So line voltage by root 3 whole square, we are going to get KV square by 3. So this is another equation. So these are the two equations that you have to remember, and then we are going to compare with the delta connection also. So this is the star connection on the stator. So this is the impedance of the each stator winding, and this is the line voltage that we are going to give. The phase voltage is equal to line voltage by root 3, and these are the line currents. So in a star connection, line current is equal to phase current. Because if you connect the stator in the delta connection, it is also called as the direct online connection. Then what is the phase current? Phase current is equal to phase voltage by impedance of the phase winding, which is V phase by Z. While in delta connection, phase voltage is equal to line voltage, so which is V by Z. And all I told you, in delta connection, line current is equal to root 3 times the phase current. So line current is equal to root 3 times the phase current. So root 3 times the phase current is equal to root 3 into V by Z. So these are the equations that you have to remember. So therefore, and already told you the starting torque is always directly proportional to phase voltage whole square. If you remove this proportionality constant, you have to keep your constant K into V phase square. In a delta connection, line voltage is equal to phase voltage. So therefore, V square. So V is the line voltage. So now these are the equations that we are going to get, and now we are going to compare the equations. So this is basically the stator winding. We are going to connect in delta. So line voltage is equal to phase voltage, and line current is equal to root 3 times the phase current. Whatever the starting current in the star, the starting current in delta, we know the two expressions. If you divide this one, we are going to get 1 by 3. So therefore, the starting current in the star connection or star delta is equal to 1 by 3 times the starting current of delta dy. Similarly, if you do the ratio of the starting torque of star connection by starting torque of delta, we know the two equations, just do the division, then we are going to get 1 by 3. So starting torque with respect to star connection is equal to 1 by 3 times the starting torque with respect to delta. It is also called as the dy. So therefore, finally we can say the starting current with respect to star delta is equal to 1 by 3 times the starting current of dy, or starting torque because of star delta structure is equal to 1 by 3 times the starting torque of the dy. So these are the things that you always have to keep in your mind. So now we are going to solve the other question. See the question here. A 3 volt adapter using a half-wave rectifier must supply a current of 0.5 ampere with a maximum ripple voltage of 300 millivolt. For a frequency of 50 Hz, the minimum required smoothing capacity is. So basically there is a load of 3 volt adapter. Here we are going to use the half-wave rectifier in order to charge this adapter. So the average value of the load current is 0.5 ampere and the maximum ripple in the output voltage is 300 millivolt and the supply frequency is 50 Hz. Then what is the minimum smoothing capacitor required to get a ripple voltage of this value? So out of the 4 options, option C, 0.0335 farad is the correct solution of this question. So let's solve this numerical. So basically this is the half-wave rectifier. So we are going to keep a smoothing capacitor in parallel with respect to load. So therefore this is the supply voltage of frequency 50 Hz. It's a half-wave rectifier. And here the load is having the output voltage of V0. And the average value of the load current is I load is called as the average value of the load current. Then here VR is called as the ripple in the output voltage, which is 300 millivolt. Already they are given in the question. And now here in the question they are given the load current is 0.5 ampere, the average value of the load current is 0.5 ampere, and the ripple voltage is equal to 300 millivolt, and the frequency of the supply is equal to 50 Hz, and the load current is equal to 0.5 ampere. So this is the formula that you have to remember. The ripple voltage is equal to the average value of the load current by supply frequency into capacitance. So we know each and every value except capacitor. So C is equal to I load by VR into F. So if you substitute all the values, I load is equal to 0.5, F is equal to 50 Hz, VR is equal to 300 millivolt. So if you solve this one, we are going to get the value of C, which is 0.0333 farad. So this is the formula that we always have to remember, which is the ripple voltage is equal to average value of the load current by supply frequency into capacitance. But I will give you the detailed explanation, or we can say the derivation of this formula also. But in examinations I request you to remember, because it is very hard to derive this one. But still you have to remember this one. So this is the formula. But let me tell you the concept behind this formula. So this is the concept. You can see clearly this is a half-wave rectifier. There is a diode. This is the input voltage. It's a capacitor, smoothing capacitor we are going to keep across the load resistor RL. So this is the output voltage V0 of t. This is the capacitor voltage Vc of t. As both are in parallel, so V0 of t is equal to Vc of t. So this is I0 of t. So therefore this is Ic of t and this is IRL of t. As you can see clearly, I0 of t is equal to Ic of t plus IRL of t. So if I apply the average values, average on both sides, I0 average is equal to Ic average plus IRL average. But Ic average is always equal to 0 because current in a capacitor, the average value is always equal to 0. Similarly for inductor, the average value across the is always equal to 0. Similarly, the average value of the voltage across the inductor is always equal to 0, and the average value of the current in a capacitor is always equal to 0. So because of this principle, we can easily say that. This is the thing that we are going to get. So therefore, I0 of average is equal to IRL of average. So this is the input voltage. This is the VI of t is equal to Vm sin omega t. So this is the input voltage that we are going to get here. So now I am going to draw the output voltage. As initially input voltage is equal to positive value. So diode is going to get on because initially capacitor voltage is equal to 0. So therefore the diode is going to get on. So therefore whatever the output voltage is equal to input voltage. So the output voltage will follow the input voltage up to this time. But after this, if you see clearly here, after this, the voltage in the capacitor cannot change instantaneously, but the input voltage is decaying. So our output voltage is higher than the input voltage. So diode is going to get reverse bias. So it is going to get off. So therefore, simply we can say that the output voltage will decay very slowly when compared to input voltage up to this time. So from here to here, the diode is off. After here, as the input voltage is higher than the output voltage, again diode is on. Again, the output voltage is going to follow the input voltage again. Same thing is going to repeat again. So therefore we can say, let me assume this is the T1, this is the T2 and this is the T3. So from T1 to T2, the diode is off, means the capacitor is discharging its energy to the load. From T2 to T3, diode is on. So therefore capacitor is getting charged. So if this is a peak to peak time period is T, so T is same for both input voltage and also the output voltage, both are the same time period. So from peak to peak, both are having the same time period. So T is the same time period for the input voltage and also the output voltage. So you can see clearly there is a small amount of ripple. This is called as the VR. So this is the ripple in the output voltage. You can see clearly maximum minimum value of the voltage has some ripple. So VR is called as the ripple in the output voltage. So from T1 to T2, as I always tell you, diode is off. So therefore capacitor is discharging this energy to load. From T2 to T3, the diode is on. So capacitor is getting charged. So from T1 to T2, diode is off. From T2 to T3, diode is on. So now we are going to do the analysis of this one. I already told you the output voltage is always equal to the capacitor voltage and the input voltage is equal to Vm sin omega t. I already told you the time constant of the RC circuit should be always higher, means RC should be only large. It should be large only when mod of X is always lesser than mod of RL, because X is equal to 1 by omega C is less than RL, means if you take C here, we are going to get RL into C is always greater than 1 by omega. So only at this condition, whenever the mod of X is less than RL, whenever we are going to get time constant of RC circuit is higher, so the output will become very less when compared to input voltage. Then only it is possible. I have already told you T is the time constant for the same for both input voltage and also the output voltage. Then total time T is equal to T3 minus T2 plus T2 minus T1, which is equal to T3 minus T1. I have already told you T3 minus T2 is called as the diode is on there, means capacitor is charging. So charging time. T2 minus T1 means that diode is off there. So therefore capacitor is discharging. So capacitor is discharging. I have already told you discharging time is very higher when compared to charging time. So we can assume the total time period is nearly equal to discharging time. I already told you the discharging time is very higher than charging time. So we have to assume the overall time is nearly equal to discharging time. So what is omega? Omega is equal to 2 pi into input frequency is equal to 2 pi by T. So VR is called as the peak to peak ripple voltage in the output voltage. So basically peak to peak ripple voltage in the output voltage. So now the diode is off. So whenever the diode is off, the capacitor is discharging its energy to the load. So whenever the diode is off, the capacitor is discharging its energy to the load. So what is the amount of charge? It is given in the discharging time period. Delta Q is equal to C into the change of voltage in the discharging mode is equal to VR. So C into VR. So delta Q is the charge given by capacitor to the load in the when V is equal to off, and also the amount of change in the output voltage is VR. So that's the equation 1. Similarly, you can write in the other format also delta Q is equal to the average value of the output current into discharge time. So as I already told you, the discharge time is nearly equal to overall time. So this is the equation 1, equation 1. So both are same, S are equal. So RHS also we have to repeat. So C into VR is equal to I naught DC into T. So VR is equal to I naught DC into T by C. So T is nothing but 1 by F. So we are going to get average value of the output current by frequency into capacitor. So finally, the ripple voltage is equal to the average value of the output current by F into C. So this is the actual derivation of this formula. So but I request you to remember this formula, because deriving this formula in the exam is a very critical case. So I request you to remember this formula, which is the ripple voltage is equal to the average value of the output current by supply frequency into capacitance. So now we are going to solve the other question. See the question here. Which of the following statements with regard to DC machine are not correct? So here they are given some statements regarding the DC machine and we have to choose which statements are not correct. Statement 1. Armature reaction decreases the flux under the leading pole tip in a generator. Statement 2. Resistance compression is generally used in the fractional kilowatt machines. Statement 3. The polarity of the interpole is opposite to the main pole ahead in the directional rotation for a generator. So these 4 options, option C is the correct statement, which is 2 and 3 are the incorrect statements, because always I already told you in a DC machine's concept, in a DC machine or we can say in a DC generator, the armature reaction decreases the flux under the leading pole tip and increases the flux under the trailing pole tips. Whereas the resistance combination is generally used only for the low fractional kilowatt machines. Only for the low fractional kilowatt machines only we are going to use the resistance combination is generally used only for the low fractional kilowatt machines. For high fractional kilowatt machines we go for the voltage computation. And also the polarity of the interpole is in the same direction of the main pole aid in the direction of rotation for a generator. See, I've already told this important point also, which is the polarity of the interpole is in the same direction to the main pole aid in the direction of rotation for a generator. So, but they are given opposite, so it is a wrong statement. So now we'll discuss something more about this one. Statement 1 is correct and statement 2 and statement 3 are wrong. So 2 and 3 are the wrong statements. So now we'll discuss each one in a very detailed manner. The correct statements are: armature reaction decreases the flux under the leading pole tip in a generator. So I can say that whatever the armature reaction, basically it is going to decreases the flux under the leading pole tip in generator and increases the flux under the trailing pole tip in a generator. Or at the trailing pole tip the armature flux adds the main field flux, and at the leading pole tip it is opposes. Therefore strengthening effect at the trailing pole tip and weakening effect of the leading pole tip. So therefore we can say whatever the armature reaction in the generator, always at the trailing pole the flux will be more when compared to at the leading pole. Now there comes the second, is called as resistance computation. So this method will be suitable for small fractional kilowatt machines only. I have already told you this resistance computation is basically used only for small fractional kilowatt machines. Means we are going to use the brushes of huge amount of resistance. So we are going to make the brushes of huge amount of resistance only for the low fractional kilowatt machines only. So this method is suitable for small fractional kilowatt machines. Means basically the brushes that we are going to choose, we are going to make of huge amount of resistance to withstand the sparks at the computation. So therefore the resistance computation means we are going to make the brushes of huge amount of resistance to withstand the sparks at the computation process. So this method is suitable only for the small fractional kilowatt machines only. So whereas voltage or EMF computation by using interpoles or competing poles or common poles, this method is suitable for normal and the large rating machines except for the fractional kilowatt machines. I have already told you very important point. Voltage computation or the EMF computation means we are going to reduce the voltage at the computation coil. We are going to reduce with the help of interpoles or competing coils or competing poles or compoles. So by this we are going to reduce the armature reaction, or we are going to reduce the reactance voltage across the computation. So therefore the spark can be reduced. All these things I have already told you. So therefore by using the interpoles or competing poles or compoles, this method is suitable for normal and the large rating machines except for low fractional kilowatt machines. So finally we can say for low fractional kilowatt machines we go for the resistance computations, and for high rating machines we go for the voltage or the EMF computation. Now let me tell you what is the actual meaning of armature reaction. See, the effect of armature flux on the main field flux is called as the armature reaction. Armature reaction means the effect of the armature flux on the main field flux is called as the armature reaction. Means the effect of the armature flux on the main field flux means the armature flux is going to distort the overall magnetic flux. It is called as armature reaction. So what are the effects of the armature reaction? Because it is going to decrease the cross, it is going to have the cross modulation effect, means distortion of the air gap flux, therefore sparking at the brushes. So because of this cross modulation, there is a distortion of the overall air gap flux. So because of this, there is a sparking at the brushes. So now then comes the other, which is called as the demagnetization, means the reduce of net flux. In the generator, the generated voltage and the terminal voltage will decrease. In motor, speed will increase and the torque will decrease, because demagnetization means the overall flux will reduce. So therefore in the generator, that generated voltage will decrease. So therefore the terminal voltage will decrease. Similarly in case of motor, the speed will increase, because as the flux decreases, the speed will increase. As the flux decreases, the torque also decreases. So this is a very important point. So therefore the effects of armature reaction are the cross modulation and also demagnetization. So with the help of cross modulation, there is a distortion of the air gap flux. So therefore if you keep the brushes at the GMA, then definitely sparking is going to get occur, because MMA is moved by a small amount of flux with respect to GMA. And the second effect is called as a demagnetization, means there is a net reduction of total flux. So because of this, for a generator, the generator voltage will decrease and the terminal voltage will also decrease. Whereas in the motor, as the flux decreases, the speed will increase. As the flux decreases, the torque will also decrease. So these are the side effects of this because of the armature reaction. I have already told you some important points. At the trailing pole tip, the armature flux is the main field flux, and at the leading pole tip opposes, therefore strengthening effect at the trailing pole tip and weakening effect at the leading pole tip. So I have already told you very important point. At the trailing pole tip there will be huge amount of flux. At the leading pole tip there is a less amount of flux in the generator. So armature reaction decreases the flux under the leading pole tip in the generator. So I already told you, under the leading pole tip in generator always flux should be very less, but under the trailing pole tip the flux should be very higher. And I told you what is the resistance compression means. The resistance compression is done by providing high carbon brush resistance. I already told you means you have to make a high carbon brush resistance so it can withstand the sparking. The brush resistance is in the series with the coil under the compression process. So whatever the brush resistance, it is in series with the coil which is undergoing the compression. So if the resistance of the brush is high, then the time constant of the current in the coil is reduced, that is the current reversal becomes very faster. So therefore, now it can withstand the spark. So therefore, the current reversal can happen within a small amount of time Tc. If it happens within a small amount of time Tc, then everything is good. If it is not happening means then there is a spark. So always under the NME, the overall flux is equal to 0, the EMF is equal to 0. So at that time, the current should reverse its direction. If it is reversing in the time Tc, time constant Tc, then no spark you are going to get. If it is not reversing means yes, there is a spark you are going to get at the brushes. So you have to make the brushes of huge amount of carbon brushes at a high resistance so they can withstand the temperature. They can withstand the spark. I have already told you this resistance compression is used only for the small fractional kilowatt machines, whereas for the high fractional kilowatt machines we go for the voltage conversion or the of compression. So now we discuss another concept which is called the interpoles. I have already told you interpoles are used to reduce the cross modulation effect of the armature reaction. I have already told you interpoles are basically used for reducing the cross modulation effect of the armature reaction. And the polarity of the interpole is in the same as that of the main pole ahead in the direction of generator rotation. I have already told this point. The polarity of the interpole is in the same as that of the main pole ahead in the direction of generator rotation. And the polarity of the interpole is the same as that of the main pole behind, main field pole behind in the direction of rotor rotation. These things I will discuss now in a very detailed manner. Carefully, there is a generator. Let me assume is a generator. I am going to rotate the generator in the clockwise direction. And in the clockwise direction, I am going to rotate the generator. This is a mechanical torque. So always electrical torque will be always opposite to the mechanical torque. So electrical torque will be downward. So I already told you very important formula. F cap is equal to I cap cross V cap. Here F is called as the electrical force. So now I want to find what is the direction of the current in this wire. So field is in this direction and the torque is in the downward because moving in the clockwise means this wire will face a torque in the downward direction. So force is downward and the field is here. So what the current should be inward. Remember I cross V, you are going to get the vector downward. Whereas here the mechanical torque is downward, so electrical torque will be upward. So therefore the current should be down. Remember I cross V. You are going to get the force in upward direction. So therefore, in the north pole, near the north pole, the conductor will have current in inward and here current is outward. Inward means cross, outward means dot. So therefore, now I am going to use a bunch of connectors, north pole, south pole. You can see clearly the connectors near the north pole will have cross mark and connectors near the south pole will have dot marks. So these are the pressures. So now you can see clearly, if you apply the right hand thumb rule, if you keep your thumb inside this conductor and if you pull your fingers, the flux in this direction. So now if you keep the thumb in the direction of the current and if you pull your fingers, you are going to get the magnetic field in this direction. So this is the armature flux. So armature flux is in the downward direction. So this is the main field flux, this is the armature flux. So now you can see clearly, I want to oppose this one. Means I have to keep a north pole here and south pole here. So now flux is from down to up. So this field is going to oppose this flux. So therefore it is going to get neutralized. You can see clearly I am rotating in this direction. So this will become leading pole tip, trailing pole tip, leading pole tip and trailing pole tip. So now you can see this is the main field flux and this is the armature flux. Then the retrogression of these two fluxes is called as the resultant flux, which is called as a phi r. So phi r is called as the resultant flux. L is called as a leading pole tip and T is called as a trailing pole tip. Now you can see clearly this is the trailing pole tip. So these fluxes, so the overall flux will now become like this. So therefore you can see at the trailing pole the flux will be very higher when compared to leading poles. So flux will be very higher at the trailing pole when compared to leading pole. So in this way I am going to rotate the generator. So therefore this is called as the an axis which is perpendicular to the overall flux is called as the MNA. So this is the action of MNA. So you can see clearly MNA is in the same direction of rotation of the generator and phi is called as the phase angle between the GN and the MNA. So whatever the coil under this MNA, whatever the coil which is under the MNA will always have the EMF 0. So now we have to move the distance to this MNA axis. So this is a very important point. So we can say, I can conclude that very important point that I am going to conclude now, which is always in generator, the trailing pole tips are going to get oversaturated. The flux will be very more when compared to leading pole tips, and the MNA is always going to rotate in the same direction of rotation of the generator. And one more important point in generator is you can see clearly as I am going to rotate in this direction. So this is the south pole. These are south pole. So whatever the main field pole polarity is same as of the top the interpole in the direction of rotation. So listen carefully. In the direction of rotation, whatever the field polarity is same as the polarity of the interpole also. So listen carefully. If I am rotating the generator in this direction, so the direction of the polarity of the interpole is same as the polarity of the head polarity of the main field pole. So this is a very important point. The polarity of the interpole is same as that of the main pole head in the direction of generator. So therefore, whatever this polarity same as this one. So therefore, the polarity of interpole is the same as that of the main pole head in the direction of generator rotation. So this is the concept regarding the generator. Now let me tell you regarding the motor case. So you can see clearly this is the motor. I will try to rotate in the anti-clockwise. Now so listen carefully. This is the north pole, this is the south pole. And what I told you, I am going to pass the current in this direction. So I already told you F cap is good, I cap was V cap. So current in this direction, field in this direction. So I cross base, the forces downward, electrical forces downward. For here current is in this direction. So therefore I cross B, I is here, B is here. So I cross base, torque is upward, force is upward. So this is going to rotate in the anti-clockwise direction. So I already told you, so this is will become leading, trailing, leading and trailing. So this is the way I am going to draw the graphs. So whatever the conductors near the north pole will have current inward means cross, and whatever the conductors near the south pole will have current in the outward direction is dot. So now we are going to see this one. So this is the conductors near the north pole will have cross mark and the conductors near the south pole will have dot. So now I already told you, if you keep your thumb in the direction of the current and if you hold your fingers, so you are going to get the flux in this direction. This is called the armature flux and this is the main field flux. So you can see clearly that here we can say this is the fluxes from up to down. So we have to approach this one. So definitely the interpole here should be north pole and south pole. So flux will be from down to up. So this is flux is opposite to this flux. So we are going to reduce the armature flux. So we can say this is the field flux, this is the armature flux. The integration of these two fluxes is called as the resultant flux. So which is a resulting air gap flux. So you can see clearly this will be from here to here. So now leading pole tips are going to get oversaturated in compared to trailing pole tips in a motor. And always you can see the polarity of the interpole is always in the behind direction of this main pole head. We can say behind the main pole head of the rotation. So listen carefully, whatever the polarity of the interpole is always same as the behind the rotation of the main field pole. Whereas here in the generator it is ahead of the rotation of the generator, whereas here it is behind the rotation of the motor. So whatever the polarity of the interpole is always same as the behind the rotation of the main field pole. So now this is the overall flux that we are going to get. So this is the overall flux distribution we are going to get between the poles. So leading pole tips are going to get oversaturated. So if I draw an axis which is perpendicular to the incident flux is called as the MNA. So this is called as the MNA. So now you can see clearly from this one, in a motor, always MNA is always in the opposite direction of the rotation of the motor, and always the leading pole tips are going to get oversaturated in the motor, and always whatever the polarity of the interpole is always behind the rotation of the motor. So these are the important points that you always have to understand. So now we are going to solve the other question. See the question here. Consider the following statements with regard to synchronous machine. Statement 1. The armature and the field MMF rotate with the same speed. Statement 2. For zero power factor lagging current, the armature MMF demagnetizes the main field in an alternator. Statement 3. For zero power factor leading current, the nature of armature MMF is magnetizing in the motor. Statement 4. For a silent pole machine, XQ is equal to XS. The correct statements are, see, statement 1 and statement 2 are only correct, but statement 3 and statement 4 are wrong. So because here I already told you, which is the armature MMF and the field MMF should always rotate in the same direction with the same speed, or we can say the relative speed between them should be always equal to 0, then only a non-zero torque is going to get produced. Otherwise we are going to get the zero torque. So statement 1 is correct. And also for the zero power factor lagging current, the armature MMF is going to demagnetize the main field in case of alternator, whereas for zero power factor leading current, the nature of the armature MMF is also demagnetizing in the motor also. It is also demagnetizing, not the magnet, it is a demagnetizing in the motor. Statement 3 is wrong. For a silent pole machine, XQ is not equal to XS. This is only for the cylindrical pole machine, only XQ is equal to XS. For a silent pole machine, XQ is not equal to XS. So only statement 1 and statement 2 are the correct, and statement 3 and statement 4 are wrong. So now I'll discuss something more about this one. As I already told you, statement 1 and statement 2 are only correct, and statement 3 and statement 4 are wrong. I told you, the armature MMF and the field MMF rotate with the same speed in the same direction. So these two MMF are stationary with respect to each other. Then only non-zero average torque is going to get produced. Otherwise, we are going to get the zero torque. So always the armature MMF and the field MMF must rotate with the same speed in the same direction. Then only we can say these two MMFs are stationary with respect to each other. Then only we are going to get a non-zero torque, non-zero average torque. Otherwise, we are going to get a zero torque. So statement 1. So now for zero power factor lagging current, the armature MMF is going to demagnetize the main field MMF in an alternator. So this is a point I already told you. For zero power factor lagging current, the armature MMF is always going to demagnetize the main field MMF in an alternator. Now for zero power factor leading current, the nature of the armature MMF is demagnetizing in the case of synchronous motor. So it is always demagnetizing in the case of synchronous motor. As I already told you, for a silent pole machine, always XD is always greater than XQ. XD is called as the direct axis reactance and XQ is called as the coordinate axis reactance. XD is always greater than XQ. So as XD is equal to Vmax by I minimum, and XQ is equal to V minimum by I max. So XD is always greater than XQ. So XD is equal to Vmax by I minimum, and XQ is equal to V minimum by I maximum. See, XT and XQ are present in the silent pole alternators where XD is greater than XQ. These two reactants are present due to two different air gap lengths in polar region and also in the interpolar region between poles. So, in order to make XD and XQ equal, all you need to do is basically choose for the, you have to keep the, see, basically I already told you in the silent pole machine, the air gap in silent pole, the air gap between the rotor and the stator is not same, only it is different, it is a varying. So because of that only we are going to get the two reactants. One is called the direct reactance and the coordinate axis reactance. As I already told you, direct axis means it is the axis on the poles is called a direct axis, and the coordinate axis means the axis which is perpendicular to the direct axis called the coordinate axis. So therefore, XD and XQ are going to present in the silent pole alternators where XD is always greater than XQ. These two reactants are present due to two different air gaps in the polar region and also in the interpolar region. Polar region is also called as the polar region is also called as the direct axis, and the interpolar region is also called as the Q axis. So in order to make the XD and XQ equal, then all you have to do basically is to make the machine as a uniform air gap means cylindrical rotor. So all you need to do is to change that 7-pole machine into a uniform air gap machine such as cylindrical rotor alternator. Then as the air gap becomes uniform and will not have any saliency, and you will always have XD is equal to XQ is equal to XS. So this is the point you always have to understand. In a 7-pole motor, so you can say clearly this is the stator and this is the rotor. So because of this, what is going to happen? Whatever the axis on this poles is called as the direct axis or D axis, or we can say polar axis, and whatever the axis which is perpendicular to the direct axis is called as the Q axis or coordinate axis or the interpolar axis. So between these two, the gap is very less, but between these two, the gap is very high. So because of these two, whatever the reactance is called as direct axis reactance, and between them, this is called as the coordinate axis reactance. XD is always greater than the XQ. These things I have already told you. So therefore, if you want to make if you keep a uniform air gap between the stator and the rotor, then always XD is equal to XQ is equal to XS. Only in the case of cylindrical rotor. That is possible only in the case of cylindrical rotor. Whereas in the non-cylindrical rotor or the 7-pole rotor, XD is not equal to XQ is not equal to XS. That is what I am trying to tell you. Direct axis gap between rotor and stator is less than the coordinate axis air gap. So the current required for magnetisation is less in case of direct axis, because you can see this gap is less when compared to this gap. So whatever the current required here is very less when compared to here. So here you need less amount of current, but here you need a huge amount of current. So therefore, XD is equal to Vmax by I minimum and XQ is equal to V minimum by I max. That is the reason you need minimum current for XD and maximum current for XQ. That is the reason XD is always greater than XQ. XD is called as the direct axis reactance and XQ is called as the coordinate axis reactance. So now we are going to discuss some more important things. Here basically we are going to see the power factor. Power factor is called as the cos theta. Theta is the phase angle between the V and IA. So V and IA is called the theta. Theta is called the power factor triangle, which is same for both the synchronous motor and also for the synchronous generator. So this is basically synchronous generator or alternator. Since I have already told you in alternator always E is always going to lead the V. Irrespective of E and V magnitude, always E is going to lead the V. And in case of synchronous motor, always V is always going to lead the E, irrespective of the magnitude of the V and E. So always in the alternator E always leads V. In case of synchronous motor, V always leads E. So suppose for UPF load, then what is going to happen? For alternator, you are going to get cross modulation. For synchronous motor also, we are going to get the cross modulation. Whereas for ZPF lag, we are going to get the demodulation for the alternator and we are going to get the modulation for the synchronous motor. Whereas for zero power factor leading load, here we are going to get the modulation for alternator and we are going to get demodulation for the synchronous motor. Whereas for point power factor lagging load, for alternator we are going to get, which is partly cross modulation and partly demodulation. Whereas for here we are going to get partly cross modulation and partly modulation we are going to get. Whereas for pointed power factor leading load, we are going to get for alternator, we are going to get partly cross modulation and partly modulation. Whereas for synchronous motor, we are going to get basically partly cross modulation and partly demodulation. So these are the things that you always have to keep in your mind. I have already told you, if you know the analysis of alternator, just for that load, for the same load, just you have to reverse the current IA by 180 degree and do the analysis, then we are going to get the analysis for the synchronous motor. Listen carefully, whatever the analysis we did for the motor, for the alternator, just reverse the current IA by 180 degree and do the analysis, then we are going to get the analysis for the synchronous motor for the same power factor of load. So this is the concept that you always have to keep in your mind. So now we are going to discuss another question. See the question here. Consider the following statements with regard to synchronous machine. Statement 1. Damper windings are used to prevent hunting. Statement 2. Excess calculated at higher exciting currents is larger than that at the lower excitations. Statement 3. Synchronous motors are preferred for driving loads requiring high power at low speeds. Statement 4. Star delta starters are used to start synchronous motors. The correct statements are, so out of these 4 statements we have to choose which are the correct statements, which are the 1 and 3 are the correct statements and 2 or 4 are the wrong. Listen carefully. Always diagonal warnings are used for preventing hunting in both the synchronous motor and also in the synchronous generator. And whatever the excess which is connected at the higher exciting currents is always lesser than that of the lower excitations. Whereas the synchronous motors are always going to prefer for driving loads requiring high power because at low speeds. At low speeds we are going to use a synchronous motor, and for high speed applications we go for the induction motor. That is the reason induction motors are more we can say more popular than the synchronous motors. And the star delta starters are basically used for the induction motors but not for the synchronous motors. So for synchronous motors we are going to use a damper warning for starting, and there are 2 other methods by which auxiliary motor or the pole motors. By this we can start the synchronous motors, but the star delta starters are basically used for the induction motors but not for synchronous motors. So we can say 2 and 4 are wrong, so 1 and 3 are correct. So now discuss something more about this one. So I already told you statement 1 is correct, statement 2 is wrong, statement 3 is correct, and statement 4 is wrong. So now discuss something more about this one. Diagonal warnings are used to prevent hunting in synchronous machine. I already told you diagonal warnings are going to prevent the hunting in synchronous motor and also synchronous generator. In the synchronous motor they are going to prevent hunting and also they are going to provide the starting torque. Whereas in the case of synchronous alternator, then we are going to prevent the hunting, and also they are going to prevent the negative sequence field currents also they are going to remove this one. As you can see clearly, see I already told you excess at the higher exciting currents is always very less because of the saturation. So therefore excess at the higher exciting currents is always decreases because of saturation. You can see clearly this is called as the open circuit voltage and this is the short circuit armature current with respect to field current. So this is the OCC graph and this is the SSC graph. So at the open circuit, this is the graph that we are going to get, and this is the short circuit graph. So if we do the ratio of these 2 things, we are going to get the synchronous impedance and synchronous reactance. Synchronous impedance is nothing but it's a ratio of these 2 graphs for each and every constant value of IF. For the constant value of IF, we have to do the ratio of these 2 corresponding things. But after mean voltage, the current increase is very higher, but the voltage increase is very less because of saturation. So the ratio is very less because E is less when compared to IA. So therefore the ratio will decrease. So therefore simply we can say that here. So this is the graph that you are going to get. So you can see clearly the magnitude of the synchronous impedance is very higher at the lower exciting currents, but as the exciting current increases, you can see it's decreasing. It is decreasing. So therefore the excess at the higher exciting currents is always lesser when compared to lower exciting currents because of the saturation effect. As I already told you, the magnitude of the synchronous impedance is the ratio of the open circuit phase voltage by short circuit armature current. These are the per phase values. These are the basically phase values. This we are going to get from the OCC graph, and this we are going to get from the SSC graph. At a constant value of IF, we have to do the ratio of these 2 things. As I already told you here, while silent pole synchronous motor are preferred for low speed and high power because it develops more power due to extra reactance power. I already told you silent pole synchronous motors are basically used for the low speed applications, whereas the induction motors are used for the high speed applications. So that is the reason induction motors are very popular than synchronous motor. And also synchronous motor are going to prefer for low speed applications, and it has a huge amount of power because of the extra fact which is called reactance power. So this is called this extra power is called as the reactance power. Because of this extra reactance power, the overall power is very high. So therefore synchronous motor has the huge power ratings because of this extra reluctance power. So therefore silent pole synchronous motors are preferred for low speed and high power because it develops more power due to extra reluctance power. So because of this extra reluctance power, the overall power value is very higher. So P is equal to E by Xs into sin delta plus V square by 2 into 1 by Xq minus 1 by Xt into sin 2 delta. I already told you Xp is always greater than Xq. So because of this reason only 1 by Xq minus 1 by Xt. So therefore 1 by Xq is always greater than 1 by Xt. So because of this extra factor, the overall power is very higher for synchronous motors. So I already told you synchronous motors are used for low speed applications, whereas the induction motors are used for the high speed applications. Because of this reason only induction motors are more we can say more powerful than the synchronous motor. And already told you pony motors or auxiliary motors are used to start the synchronous motor. And already told you synchronous motors are not self-starting motors. So we have to start them by manually. So it is called the pony motors or the auxiliary motors by which we are going to start this synchronous motor. See, whereas starter starter is used for the 3-phase induction motor. I already told you starter starter because initially whatever the currents are very high in the induction motor, to remove the huge amount of current, we are going to use the star delta starter. Because of that, starting currents we are going to reduce. So we are going to protect the windings. So star delta starter we are going to use in the 3-phase induction motor, but not in the synchronous motor. Let me tell you what is the purpose of damper windings in the alternative of the synchronous generator, which is they are going to eliminate the hunting and also to suppress the node sequence fail. I already told you the purpose of damper winding in the alternators are basically to eliminate the hunting and also to suppress the node sequence fail. And the purpose of damper winding in the synchronous motors are basically to eliminate the hunting and also for starting purpose. So they are basically eliminate the hunting and also for starting purpose to provide the starting torque. Eliminating hunting means suppose suddenly load is decreased. So speed will be higher than synchronous speed. Then the induction generator torque is going to act in the opposite direction of the rotor rotation. So speed will decrease to ns. Similarly, suppose the load is increased, so speed will decrease nr less than ns. Then the induction motor torque is going to get act in the directional rotation of the rotor. So it will increase the speed, so therefore nr will become equal to ns. So this is the basically it is hunting for a new stable point. It is called as the whenever there is a sudden change in load, the motor is going to hunt for a new stable point. It is called as the hunting. The starting methods of synchronous motors are, I already told you, synchronous motors are not self-starting. They are not self-starting. So we have to do some techniques to make them self-start, which are the auxiliary motor is also called as a pony motor starting. Our second method is called as the induction motor starting, or the starting with damper winding on rotor. So if you keep a damper winding on rotor, initially it is going to start like induction motor, but finally it is going to act like a synchronous motor. So we can call it as a damper winding on the rotor or induction motor starting. Another method is called as a synchronous induction motor starting. So these are the 3 methods by which we can start the synchronous motor. One is called as the auxiliary, we can say pony motor or auxiliary motor. Second one is the keeping a damper windings on the rotor, and the third method is called as the synchronous induction motor starting. So these are the 3 methods by which we can start the synchronous motor. See, finally, 3-phase and 2-phase induction motors are self-starting motors. See, 3-phase and 2-phase induction motors are always self-starting, means from 0 onwards, starting torque is not equal to 0, so these are self-starting. Whereas single-phase induction motor is not self-starting. So that is the reason we go for the extra winding, which is called as the auxiliary winding. So we are going to use for starting purpose. But after reaching certain speed, we are going to remove that starting winding. So therefore, it is going to initially single-phase induction motor is going to act like a 2-phase motor, but after certain speed, we are going to remove the starting winding. So it is going to act like a single-phase induction motor. So again, 3-phase and single-phase synchronous motors are also non-self-starting. So starting torque is always equal to 0. So by using these techniques and already mentioned, we are going to make them self-start. So generally speaking, 3-phase and 2-phase induction motors are always self-starting, and single-phase induction motor is non-self-starting, and the 3-phase and single-phase synchronous motor are also non-self-starting. So therefore, 3-phase and 2-phase induction motors are the self-starting motors. Single-phase induction motors are the non-self-starting or not self-starting motors, and the 3-phase and single-phase synchronous motors are also not self-starting motors. So by using certain techniques, we are going to make them self-starting. All these things I already told you in the machine concepts classes.